Nazywam się Grzegorz Bunda i jestem naczelnikiem Wydziału Informacji Społecznej w Departamencie Energii Jądrowej w Ministerstwie Klimatu i Środowiska.
I represent the Department
Przyjemność przedstawić Państwu
Nuclear
pana
Energy
ministra
with
Adama
the Ministry of Climate and Environment.
Do Komitetu Programowego, Komitetu Organizacyjnego oraz do Państwa uczestników 11 Międzynarodowej Szkoły Energii
has been produced.
Szanowni Państwo,
from the ministry. Let me read it out at the moment. Ladies and gentlemen, our ministry has been involved in co-organizing of the International School for Nuclear Power. Our goal is to ensure a competent staffing for the Polish nuclear power program. I'm really grateful for you that you have joined the program, having become a part of it, an important part of it. Poland has invested in new power units in order to increase the existing power capacities and exchange the old or obsolete generation production units into pure energy sources, such as renewables and non-emission or emissionless nuclear power plants reinforce the power safety of Poland based on diversification of the fuel resources and directions of the transmission of energy carriers and transmission directions. In this case, rendering ourselves independent from Russia and supplies from that direction are a major thing politically, geostrategically, and so on. The last year has been rather exceptional in the context of implementation of nuclear power in Poland. The record-breaking figure of 86% of the Poles are supportive today for the construction of nuclear power plants in our country. This is based on our survey from November last year. This high support reflects the situation on international energy markets as well as the progress in the implementation of the nuclear program having been implemented for several years now in Poland. In April 2023, an amended special nuclear act was enacted. It is an essential legal instrument to streamline the implementation of nuclear power in our country, and this law is to accelerate the process of issuing all sorts of permits, licenses, etc., streamline the process across the stages of investment activities, preparation for construction, and construction itself of the first Polish NPP. As from the very first day under the new law, the investor, which is the Polskie Elektrownie Jądrowe, that's the name of the company, has applied with the ministry for the basic decision for Poland's first NPP. On the 17th of April, Synthos Energy company submitted an analogical or parallel motion. Also, a company called PGEPA Energia Jądrowa, a joint stock company, was established for the purpose. The latter will join the construction of an NPP in Konin-Pątnów in Greater Poland region. The ministry has been active and proactive along the lines of supporting and involving Polish industry in the implementation of the nuclear program. The existing analyzers have pointed to the fact, or identified the fact, that the Polish national industry will be capable of participating in a variety of projects, areas, including infrastructure, accompanying infrastructure, machinery, production, assembly, manufacture, etc., of certain components of the so-called reactor island. The share of our industry in the first Polish realistic implementable nuclear project shall be at least 40% of the project's work. That's true for the first reactor, and up to as much as 70% of the value of the project when it comes to the further stages of it. In 2022, the Ministry has implemented a series of comprehensive trainings attended by hundreds of participants. As you see, we have accelerated quite a lot, so we wish you all the best for this particular meeting or convention and for your further proceedings. Thank you very much indeed on behalf of the Ministry. Thanks. Thanks very much to the Ministry. We join the option, the optimism, the activism around the project, obviously. Ladies and gentlemen, let me invite our co-organizer, who represents Mr. Janusz Frączek, a professor with the engineering department of the Warsaw University of Technology. To be more specific, I represent the mechanical department for power engineering and aviation. It is quite a long and complex name in itself. I tried to memorize it several times for myself. Okay. Having said that, the world of industry, science, representing the governmental administrative bodies, dear students, all of you attending, I'm addressing you dearly. My proper area is robotics, control. However, in spite of various vicissitudes of the nuclear in Poland, I'm part of the whole story. We are part of the whole story. And happily, so many of students also represented here in this room that not only have touched upon our area and our department, drawn from its proceedings, from its works, from its scientific activities in Poland over the years. So we're part of the story. Judging from the minister's words, well, the minister's representatives' words that have been read out moments ago to us, the appreciation comes from high up, which makes us feel even better, all for the better, in terms of the project and its prospects. This imbues us with hope, with great expectations, and we hope that our students will join the the project in general, the Great Polish Nuclear Project. I've read the agenda of this conference, and I believe that your contributions will contribute to increased awareness of nuclear power and expanded knowledge on the topic. Thank you very much indeed. Our department is physically not far from here, so feel invited always. Thank you very much indeed.
Szanowny panie profesorze, bardzo dziękuję za wystąpienie. Szanowni państwo, przystąpił mi również zaszczyt poprowadzenia na dzisiejszej konferencji pierwszej sesji merytorycznej. Ta sesja poświęcona jest programowi polskiej energetyki jądrowej. Będziemy chcieli zacząć tą sesję od prezentacji osoby, który z całą pewnością państwo bardzo dobrze znacie, pana Andrzeja Sidła, wieloletniego pracownika bezpośrednio
today the chief specialist with the Department of Nuclear Energy within the Ministry of Climate and Environment, has been through a variety of post positions and functions. Andrzej,
przedstawił nam pan, jak wygląda sytuacja w zakresie wdrażania programu polskiej energetyki jądrowej, zwłaszcza w udziale polskiego przemysłu.
The present day implementation status with special focus on Polish industry and its share.
Dzień dobry, szanowni państwo, ja nazywam się Andrzej Sidło. Jak zostałem wprowadzony, jestem pracownikiem Departamentu Energii Jądrowej, aktualnie w strukturach Ministerstwa Klimatu i Środowiska, czyli ministra odpowiedzialnego za plan administracji rządowej pod nazwą energetyka. Przedstawię państwu pokrótce aktualny status programu jądrowego w Polsce oraz w drugiej części omówię kwestie przemysłowe, przygotowania krajowego przemysłu do projektu. Ja myślę, że tej mapy nie ma co zbytnio omawiać. Wszyscy, którzy interesują się energetyką jądrową, wiedzą, że energetyka jądrowa na świecie jest. W Europie ostatnimi czasy trochę branża przeżywa regres, natomiast należy powiedzieć, że na świecie energetyka jądrowa jest prężnie rozwijającą się branżą. Głównie Azja, Rosja, tutaj Chiny, Indie rozwijają te technologie, budują bardzo dużo. No i na tej mapie szczególna, brakujący kraj to jest oczywiście Polska. Miejmy nadzieję, że za niedługo będziemy również tutaj członkiem tej społeczności jądrowej w pełnym wymiarze. Proszę państwa, program energetyki jądrowej w Polsce, główne cele, które stawiane są dla realizacji programu jądrowego, one są częściowo rozbieżne, jak wszyscy wiemy. Po co my w ogóle potrzebujemy elektrowni jądrowych w Polsce? No, żeby zapewnić bezpieczeństwo energetyczne, żeby zmniejszyć naszą emisyjność wynikającą z samej energetyki. No i proszę państwa, różnego rodzaju korzyści ekonomiczne. No, jak każdy tutaj zastanowi się, o co tu chodzi, to widać, że te cele są częściowo rozbieżne i my w naszych wszystkich działaniach musimy znaleźć jakieś optimum, żeby pogodzić te trzy linie działań. Aktualny program polskiej energetyki jądrowej, aktualizacja, zaznaczam, z 2021 roku nałożyła obowiązki na różne podmioty, czy to administracji rządowej, czy głównie spółkę. Aktualnie ona się nazywa Polskie Elektrownie Jądrowe, żeby przygotować całość infrastruktury krajowej w różnych obszarach do tego projektu, czyli jest takich 5 jakby obszarów, nad którymi musimy popracować, czyli kadry, przede wszystkim kadry, komunikacja i pozyskanie akceptacji społecznej do programu, infrastruktura różnego rodzaju, czy to techniczna, drogowa, kolejowa, ale też prawna. Szczególną rolę odgrywa tutaj dozór jądrowy i przede wszystkim wzmocnienie dozoru jądrowego i przygotowanie dozoru jądrowego do tego projektu. No i oczywiście jeden z elementów, który jest tutaj bardzo mocno zaakcentowany w ostatniej edycji PPJ-u, jest polski przemysł, a dokładniej przygotowanie krajowego przemysłu. To jest taka mapka, która w ostatniej aktualizacji PPJ-u została załączona jako wykaz, lista potencjalnych lokalizacji elektrowni jądrowych. Tutaj oczywiście pod pierwszą elektrownię jądrową inwestor spółka PJ w ubiegłym ubiegłym roku
PJ
bardzo
last
zaawansował
year has advanced very much its work and has submitted an application
przeprowadził różnego rodzaju
and carried out environmental studies. And as we know, the preferential two locations are on the sea. According to the nuclear law, investor is to present preferred and alternative location in the proposal. It must be in Pomerania. Lubetow Kapelin for various reasons is located as PJ. And alternative Żarnowiec on the site of the unfinished project from the 1980s. Well, ladies and gentlemen, talking about the activities focusing on the location, a lot has been happening recently, and the key entity doing all that is PJ company, with support or coordination by both the Ministry of Climate and Environment and a General Directorate for Environmental Protection. Last year, a report on environmental impact was submitted, and analysis have followed. Consultation process currently are in the very important stage of this in international transborder consultations. According to ESPO convention, Poland is a signatory to. You have to do it with all the countries that have signed the convention. We have finished different rounds, not so much of negotiation, but to explain where experts have asked questions, experts from, say, Germany, how we are planning to protect the environment. Some have already signed protocols ending, completing the process. We are still in front of several rounds, several meetings. It won't be with Denmark and Austria. It won't be easy. These countries are not among sympathizers of nuclear energy plants, so we have to expect that all sorts of detailed, in-depth questions will be asked. But we have to go through that process in order to move to the next stage of the project. As we all know, we are basically at the highest level historically of support, public support to nuclear energy. I think the last few years have been the reasons for increasing support, and last year Russian aggression in Ukraine, but also earlier years, we know that in 2021 odd things happened in European natural gas market, but also earlier. As a result, public opinion is more and more conducive towards accepting nuclear energy, even though we are historically perceived as a coal-based country with long-term traditions. But however, the public support for nuclear energy has been growing. One of the reasons is also raising awareness among the population of environmental issues. Well, it's our interest to defend the coal, but there are other aspects.
Alternative solutions to coal are being looked for. Obviously, nuclear is one of the sources of benefits in this respect, real considerable benefits. As to the Polish program, the NPPP, PPEJ works as a kind of acronym for it in Polish, mind you. Yes, the dates
Przede wszystkim należy się skupić na tym, co nas czeka w najbliższej przyszłości. I tutaj, proszę Państwa, idziemy mniej więcej zgodnie z założonymi harmonogramem, czyli w ubiegłym roku wybór technologii dla pierwszej elektrowni jądrowej. Z tego co pamiętam, to był bodajże chyba 2 listopada ubiegłego roku oficjalne potwierdzenie już komunikat Rady Ministrów, że dla pierwszej polskiej elektrowni jądrowej została wybrana technologia amerykańska AP1000, czyli technologia źródłowo
Council of Ministers of the Republic of Poland has named the American technology AP1000 as the one selected for the purpose. So all the environmental decisions, siting decisions, procedures around them have been started and going well along the lines of the procedures. Among other things, a bridge contract has been entered into with Westinghouse. The Polish company and Westinghouse being the contracting parties for determining technological, technical conditions for the project and its implementation in very rough terms. And this September, October, yet another contract with Westinghouse will be contracted for some of the key nuclear island components. The years 2025-26 are expected to see first construction, initial construction works around what is called nuclear concrete, earthworks, you know, all these sorts of things, according to the particular schedules regarding construction. Physical commencement in a word, whether the reactor will be connected by this before said year, we'll see. Hopefully, yes. And in parallel, the second and the third reactors will start being constructed within a time span of 2 to 3 years, based on cost optimization. As a target, the first MPP is going to become operational with its 3 reactors altogether within roughly the years 2030, 537, as I said before. ZPAC and PGE, those two companies several times mentioned before, signed in October 2022 a letter of intent with KHNP concerning the construction of the third nuclear power plant based on APR 1400 in Pątnów, West Poland, basically. And in April this year, having got the agreement from the Office of Consumer Protection, yet another agreement along this line was signed. The most advanced technologies as well as entities include the two mentioned. Once Orlen Synthos Green Energy is the special vehicle, special purpose vehicle established for the specific purpose in cooperation with GE Hitachi Nuclear. They're going to establish, to basically construct, set up and commission the BWRX-300 Small Modular Reactor. They have presented their maps, including locations such as Oświęcim, Stalowa Wola, Nowa Huta, in various places of Poland. These ideas will be developed in the weeks, months and years to come. NuScale American SMR is also considered, namely last month, Orlen Synthos and its subsidiaries presented a map of potential locations for the new SMRs, and KHNP has applied for siting permit. As to the involvement of the industry,
należy zaznaczyć, że my jako kraj wchodzący w energetykę jądrową, czyli nie
as
posiadający jeszcze
Poland,
tej elektrowni
being the country entering the nuclear business, is not starting from the scratch.
Pomocne, przydatne są rynki eksportowe.
Export markets are very useful. I mean, Polish companies have joined several international projects, including EU, Europe basically.
Oceniamy, że zaangażowanie krajowego przemysłu
Europe
będzie
first.
istotnym elementem
That's what is happening.
całej tej układanki,
Involvement of
całego
European
w Polsce. Oceniamy, że to
industry
przyniesie korzyści
is
wszystkim,
going to
czyli
become a
polskiej
very
gospodarce,
important element of the puzzle,
polskim firmom,
of the picture.
wzrośnie na pewno
rendering
zaangażowanie krajowego przemysłu,
all sorts of benefits, bringing all sorts of benefits
akceptacja
for
społeczna
Poland,
energetyki jądrowej i również
its
oceniamy,
workforce,
że w
its
wielu
industry,
obszarach
its
duże zaangażowanie
business,
krajowego
whatnot.
przemysłu przyniesie korzyści
Such
również
a
w
considerable
technologii jądrowych.
involvement
Nie
of
można
industry
przywieźć wszystkiego z
will
zagranicy i w wielu obszarach
be
udział krajowego
most beneficial
przemysłu jakby
to the
zoptymalizuje ten projekt,
nuclear
czyli
technology as such, based on cost optimization, based on streamlining, based on all sorts of contributions that can be made, provided or rendered locally, rather than outsourced or brought from imported from abroad. Firstly, the participation of the national, which is Polish industry, will not be limited to a declarative sphere or area, like memorandum of understanding being signed with foreign partners, Polish partners, but
bezproblemowe działanie.
The share and participation, proactive participation of Polish industry will be set up legally in the form of provisions, specific provisions, which are implementable. So we'll start from the minimum of 40% of the whole value or worth of the project with reactor number 1 and with a growth trend of up to, hopefully up to 70% at the end stage of the program. We expect to learn much along these lines, obviously, and to come in more of variety of details concerned. Late in 2021, the Minister in charge of Climate and Environment approved of the program for support of the national industry in the context of collaboration with nuclear power. This includes an optimized support of national enterprises in acquisition and implementation of, rather costly quality certification, a variety of series of information as well as training actions, promotion and support of the national enterprises internationally, streamlining of the transfer of technologies to domestic enterprises, supporting cluster initiatives, cluster projects, or other ones in order to gather a group, form groups or clusters of involved and interested enterprises, and so on.
No i jeszcze dwa takie poboczne działania, czyli zamierzamy również jakoś, jeszcze na razie się zastanawiamy jak, ale popracujemy tutaj, żeby usprawnić ten proces transferu technologii i wiedzy docelowo do polskich firm. Też również wzorem różnych rozwiązań międzynarodowych widzimy, że kraje wchodzące w energetykę jądrową wspierać różnego rodzaju czy to inicjatywy czy powstawanie docelowo jakichś izb gospodarczych
at an early stage of entering or joining a variety of nuclear programs
promowały energetykę jądrową na
that are willing to develop their nuclear business.
I teraz, proszę Państwa, wiadomo, jakie korzyści może przynieść duże zaangażowanie krajowego przemysłu w projekt. No to myślę, że chyba nie trzeba nikomu tłumaczyć. Wiadomo, że
what are the expected benefits? Well, no need again to explain the details to an audience like you, ladies and gentlemen. National involvement includes more basic and additional orders, commissions for national enterprises, more technological and organizationally advanced projects in relation to conventional power engineering or petrochemical projects, offshore projects, in particular oil gas sectors. Sometimes the time horizon is too extended, I would say, overly extended. In Finland, in France, in the United States, we've seen all sorts of delays and causes behind them. But sometimes on the side of the subcontractors, especially, it pays back because it gives them kind of horizon stability, which works as a magnet, attracting industries from abroad, including from Poland, for instance, in joining those, apparently unstable and long-lasting projects. But on the other hand, there's an opportunity to learn much. Polish companies have a long, medium-term contracts, like 5-7 years expectedly to go, drawing as much as possible from them. So there are, pros and cons. Pros coming first, in our view, in this picture. We have mapped the competencies of the Polish industry in the context of nuclear power. This is a kind of matrix here, which in brief shows you
co moglibyśmy robić tu i teraz, dzisiaj, jakbyśmy dzisiaj rozpoczynali budowę tej elektrowni w Polsce. W sensie, jakbyśmy na przykład dzisiaj już wbijali łopatę, no to tak idąc od dołu, proszę Państwa, to szybko mówię,
the construction
to są,
of an NPP in
Państwa,
Poland
najprostsze
right
rzeczy,
now,
oczywiście prace ziemne, budowlane, jakaś infrastruktura
with a
towarzysząca,
shovel
to oczywiście to wszystko
and so
polskie
on.
firmy mogą zrobić z biegu.
All this can be done by Polish companies.
Wyżej, wyspa konwencjonalna, czyli tak powiedzmy w skrócie, wszystko to, co nie jest jądrowe. Polskie firmy też to umieją robić. Znakomitą większość polskie firmy mogą zrobić, zarówno jeżeli chodzi o montaż komponentów na budowie, produkcję praktyczną wszystkich takich komponentów, projektowanie
production, manufacture of any such components, designing any such components, all of it can be done by Polish companies. Balance of the plant, and the turbines and generators. We know that not yet any such large turbine, steam turbine, has ever been produced in Poland. This is why it has to be produced somewhere else. Sprinklers and any other supportive or auxiliary appliances. But we can learn and we can at least cooperate in producing them or manufacturing them. Well, the island, that's not an easy part, is it? Because
sprzedać swój produkt. Ale również i tutaj oceniamy,
technology
że
offerers are going to, are willing very much to sell to us, propose and ultimately sell to us their ideas, their designs, their solutions.
Przy czym zaznaczam, że to są,
However,
ta matryca jest jednocześnie
there is a variety of individual competences that we can manage as a Polish party, and we've participated in experts in Finland, Mexico, France, wherever else, and if we could do the job in such distance, faraway areas, all the better for us to do it here. So experiences pay back. What can be problematic as regards the development of nuclear competences? Simplifying.
To nie jest jakaś taka wielka bariera. Oczywiście tutaj też polskie firmy, jak chcą trochę więcej zarobić w projektach, będą musiały trochę rozbudować swoje moce produkcyjne i tak dalej. Ekonomiczne, finansowe bariery czasami są tutaj istotne, dlatego że nie zawsze polskie firmy są w dobrej kondycji ekonomicznej. Natomiast największy obszar taki problematyczny, który widzimy teraz, jest w tej części najbardziej niewiernej, czyli te wszystkiego rodzaju kadrowe sprawy, częściowo certyfikacyjne, kwestie tej jądrowej kultury bezpieczeństwa, które również w łańcuchu dostaw trzeba wdrożyć. To jest największe, proszę Państwa, najwięcej do zrobienia. Dlatego my na poziomie rządowym nasze
much still remains to be done, and at the governmental level we address a variety of preparatory actions to this particular sphere, explaining to Polish companies what we mean by quality in nuclear sector. So not just certification, but understanding of the security and safety culture. So still a lot to be done in this particular respect. Very briefly, you've probably saw a catalog that we once provided, compiled
tego katalogu to jest 2021 rok, Polish Industry for Nuclear
Energy. Polish Industry for Nuclear Energy catalog that was published in English in 2021. It is a catalog of Polish companies with nuclear references competent enough to enter the business. We've identified a whole lot of Polish companies, entities with very interesting references in the last decade, especially, which we set for ourselves as the temporal criterion. So a variety of nuclear references, especially associated with Energomontaż Północ Gdynia, that's the name of the company based in Gdynia, and the turbine body, which was machined thermally in Opole, and then it went to Darlington in Canada, serves as just one example of the many. Here, the chart shows you by sector distribution, and on the right hand side the size structures, construction, electric sector, automation, mechanical appliances, devices, manufacturers, design, engineering works, metal devices, assemblies, and so on and so forth. This gives you a rough idea, at least. The red in this map refers to where a minimum of one nuclear facility is represented in terms of Polish participation in a given project. Russia is definitely a large partner
to na pewno zmieni.
Internationally. The present day situation is changing it certainly, so we don't know how about the future. But our share has gone there as well. North America, Middle East, India, China, apart from Turkey, maybe. Britain, of course, Hinkley Point. Several Polish companies are involved there, have been involved there for some time. Some of them moved to Egypt, to Eldaba, where physical works have already been started, and the production is quite advanced there. Polish companies being part of the story already. Canada, United States, Mexico. This map still needs being updated in line with the Polish Industrial Nuclear Energy Catalogue. One of the Polish companies boasts their supplies to Andhra NPP. In Brazil, well, still no South Korea, South Africa, no North Korea, and Africa. These areas are still lacking in terms of Polish cooperation, but hopefully our future directions. As regards the Polish government's actions towards stimulation of competences of Polish industry and implementation of nuclear projects, the Polish governmental agencies, various competent ones, have implemented a whole series of information as well as training actions. Here is a short list of them. See, last year we have structured trainings, sessions for especially construction, electricity and metal sectors or branches. 2 rounds of training sessions are to be held in week 2 and 3 of June this year, and possibly in quarter 3 and 4 this year as well, for those particular industries. A whole lot of workshops, training workshops, seminars having been implemented, carried out so far, as you can see in this list, starting basically from 2015 onwards. Missions to Finland, Canada, Great Britain, business fora in Poland, parts of the picture as well, as regards stimulation of competencies of the Polish industry, as we name it. Polish companies, Polish entities have expressed great interest in
I w tym roku też mamy kilka kolejnych wydarzeń w przygotowaniu, informowaniu
third countries as well, not only
to byłoby wszystko mniej więcej, jeżeli chodzi o moją prezentację. Tutaj w prezentacji jeszcze zostawię dość dużą część o znowelizowanej ustawie prawo atomowe, ale myślę, że to by wymagało w ogóle oddzielnej konferencji, czy no, nie wiem, 2-3 godzin. Dwie rzeczy są istotne, jeżeli chodzi o tą ustawę prawo atomowe po nowelizacji. Proszę Państwa, po pierwsze jest tak, że jak zostało to wspomniane, nowelizacja usprawniła proces administracyjny i oceniamy, że bez uszczerbku na jakości bezpieczeństwa jądrowego skrócimy proces administracyjny od 12 do 18 miesięcy. To jest przede wszystkim przesunięto tą decyzję zasadniczą polityczną z końcowego etapu na początkowy proces tego łańcuszka administracyjnego. Natomiast druga rzecz, o której trzeba pamiętać, wbrew temu, co się mówi, polskie prawo atomowe to jest mniej więcej, podobnie jak w większości krajów Unii Europejskiej, jest neutralne technologicznie, czyli na mocy tej ustawy można rozpocząć licencjonowanie wszelkich obiektów jądrowych w różnych technologiach, dużych, małych i również reaktorów badawczych, bo to, co mamy reaktor Maria, licencjonowanie w sensie
Maria reactor in Świerk outside of Warsaw.
Na podstawie tej ustawy, więc informacja jest taka, że jest neutralna technologicznie. To jest
can all work and does work under the umbrella of this particular law. Thank you very much indeed. That would in brief be the picture of what I was going to present to you for the purpose of this
Panie
conference.
Andrzeju, bardzo dziękujemy za prezentację, przede wszystkim za bardzo dużą dyscyplinę czasową. Szanowni Państwo, jeżeli ktoś z Was chciałby zadać pytanie Panu Andrzejowi, to jest wyjątkowa okazja, żeby to zrobić teraz, natomiast prosimy, żeby to było krótkie pytanie. Pan Andrzej jest do naszej dyspozycji, będzie też jeszcze w trakcie przerwy
You will have time to discuss things during the coffee break or lunch break, but should you be willing to ask questions, there will be microphones to be handed to you. I can see one hand raised. Good morning, ladies and gentlemen. My name is Jacek Bałucki. 55 years of work continuing in energy, of which 14 nuclear energy sector. I have two comments talking about Denmark and Austria, who are against Polish nuclear energy sector. I've informed Madam Moskva, Mr. Sashin, when they were going to America in last October to sign the project agreement. 2 days earlier, I've submitted a short letter which was reprinted at the Postępy Technical number 4/22, where of course, I support the selection of the reactor under item 1 in the item 3 to appease France. That could be done if should Austria, that in the constitution has a provision that they not allow in Austria nuclear plants. And within the process of acceptance of transborder power plant in Poland would be against it, then we have to propose that we transfer the Vienna headquarters of the International Atomic Energy Agency to Paris. It's odd to have this energy seat or headquarters in the anti-nuclear. Austria and France is a nuclear superpower. My second item I would like to remind you of is that for 10 years, between 1980 and 1990, at the Institute of Energy, we coordinated nuclear energy programs. And talking about energy, including nuclear energy programs. And the materials collected over the 10 years, my elder friends know that they worked on them and they worked under the project. There are many things already that should be reminded. Next thing is that of a system of quality provision. It cannot be just a program such as TQM, Total Quality Management. Every corporation has a different approach to, or system to provide quality are regulated by International Atomic Energy Agency, and I wonder that there is no feel that this quality management system uniform for nuclear energy sector would be introduced. I have other comments, but that would be enough for the time being, I think. Thank you. Well, I think that in relation to Austria, it's an oddity. A country, as the only one in the constitution, has a ban on nuclear energy, but we leave it to the political discussion. I would like to clarify one thing. Few people know about how the ESPO convention operates. The idea behind it is not to convince our neighbors that we claim that nuclear energy is great and Germans or Austrians are of the opposite. It's a philosophical or ethical discussion. But the idea behind the convention is to share comprehensive information to the other country how we are going to implement the project in a safe way. This is the idea. It's not defined how, the word how, whether we have to show a certificate or something. We have to answer all the questions exhaustively. So this convention is not precise here, what unfortunately we have to do it. Back in 2013, we had the first international consultation of the entire program at the intergovernmental level. And I remember Austria and Denmark asked many quite odd questions, but we had to answer in order to obtain the approval to the protocol ending this under the consulting process. As to earlier project, Żarnowiec, unfinished, and the accumulated knowledge, we all know it's a pity it was abandoned, and we all want to utilize this knowledge to the extent possible to retrieve it, to use it, despite the lapse of time. But certain things still can be reused, reutilized. This would be my comment to your comment. Thank you very much, ladies and gentlemen. Andrzej, thank you very much for your presentation. Let us move to the second presentation. I would like to invite Mr. Piotr Dobrzyński of the Polish Nuclear Energies Limited Liability Company to tell us about the status of the implementation of the construction of the first nuclear plant in Poland. He is very experienced in nuclear energy, in great consulting companies at the European level. So his thoughts, his comments will be very valuable to us. Over to you. May I ask for my presentation? Good morning once again. A warm welcome to all of you. First of all, as a former graduate of the energy department, I'm glad to see some faces that I know. Although I don't remember this very building, it's always great to get back to your alma mater. So once again, thank you. My name is Piotr Dobrzyński. I'm Deputy Director of the Business Development Department at the Polish Nuclear Plants Limited Liability Company. I'd like to present the status of the implementation of the program of the first power plant in Pomerania. We'd like to go through three key aspects. First of all, focus on the foundations of nuclear energy in Poland and the role of PEJ, that's the Polish acronym for my company, and to discuss the current activities of our company, and many things are going on, and finally to present the next steps and priorities for next months to come. To begin with number one, it is important to give you some context to present the framework of the nuclear program where we as PEJ operate. A Polish government has provided the framework for the program to giving the guidelines how to operate. These are key three documents or legal acts presented here. Polish energy policy by 2040, providing that over half of the power generation will be zero emission sources. Polish nuclear energy program of 2020, which is a strategy document presenting the legal basis and the specific plan to program how to on the PWR technology, the first plant, and the third international agreement between Poland and the United States of America regulating joint effort to develop civil and nuclear energy sector. Let me walk you through all these to better understand our role. Our Polish energy, nuclear energy is one of the pillars provided by in this document. One of the plant energy transformation. It's number one in dark green for zero emission energy sector. Nuclear energy is mentioned as one of the key technologies other than offshore wind farms or citizens projects, local projects, plus other two pillars. Number one, about just transformation, transition of mining regions, development of new industry sectors related to renewable sources of energy, including the nuclear one. And the third pillar on the right-hand side, it's the air quality and transformation of the heat system or electrification of transport. As talking about the Polish nuclear energy program, PPEJ, it provides that by 2040, 25% of electricity will be generated by nuclear power. It determines that there will be 6 reactors to 9 gigawatts, 6 to 9 gigawatt each. And the first power plant will be constructed using the BWR3+. And we are technology, and we are a company responsible to implement, to construct, to build the first one by 350 megawatts. PPJ, other than this overarching objective, is presenting also saying why we want to develop nuclear energy. The previous speaker has already mentioned it. We're talking about energy security, and we don't have to clarify it. Bearing in mind current geopolitical situation and need to diversify the sources and to replace old coal-fired units, we're talking also about the positive impact on the climate and environment in line with the Paris Agreement or Green Deal, economic development where nuclear energy propels the development of new sector and provides new jobs and guarantees stable energy prices. These key documents regulate, in fact, our role as the Polish nuclear power plants company since March 2021, 100% owned by the state treasury, supervised by the government representative, Minister Mateusz Bergel, and since June 2021 we've been operating under the current name, PEJ Polskie Elektrownie Jądrowe. Earlier it was a different name you might have heard of. To go further, I would like to present quickly current activities of ours. I would like to start with the locations. The previous speaker has already mentioned. We have 2 possible locations, of which one is that of Lubiatowo-Kopielina is indicated as preferred one, both in the Pomeranian province, then Choczewo municipality with access to the sea, to the Baltic Sea directly, so important for the open cooling system, and Żarnowiec. Everyone of us is aware of the history of it and not on the sea, 10-15 kilometers inland, but it's a good location, also analyzed. Talking about locations, it is important to remember how big an impact such a project has for these locations, where there will be we're talking about the very location and also adjacent locations. We talk about 4 key benefits stemming from the project: guarantee of stable energy supply, also thousands of jobs created by such a project. We don't talk about the construction process only, but according to the estimates, for everyone working at the construction, between 3 and 4 to 5, it will generate the needs between 3 to 5 additional jobs in catering, hospitality, or whatever. Such projects provides economic development for the region We're talking about infrastructure, knowledge centers, as we observe in Western Europe. And of course, that's very important as well, tax revenue, increased tax revenue for local authorities and also for adjacent municipalities. And we are aware of the fact that the public is aware of all that. I don't want to go through. The previous speaker has already touched upon it. We have great support in Poland for nuclear energy, but we as PEJ focus very much on the region where we want to build the power plant. 75% support this project, slightly less than the national average, but we have this not in my backyard, as you call it. Nevertheless, it's a very high level of support, and we as a company are present, have been present from the very beginning, and you can see there's no power plant globally created without proactive involvement of respective regions. We have 3 representatives in the region, always an employee. You can visit and talk to about the project and its impact on the environment, on the region. We've organized workshops for the region about the environmental impact report to get the local public involved. So we act proactive and we get involved in the local activities. And now, talking about the key activities of ours as a company, you can summarize them under 3 key processes. These are the 3 aspects that we mentioned. The first is that very important to obtain all the necessary approvals and licenses and permits, and second, design work in agreement with the supply of technology and main contractor, and all the activities that are necessary related to all the hookups or links, all this adjacent or accompanying infrastructure that have to be there before the construction starts. So now talking about the permits, the process is quite advanced. Some milestones we have reached already during the last years or month. In March last year, 2022, we've submitted an environmental impact report to the General Directorate of Environmental Protection. In October, General Directorate has launched the transborder proceeding we've already mentioned, where we are obliged, being a member, to ESPO Convention. And last February 2023, we had a first bilateral meeting with representatives of Latvia, with the positive impact. Between March and April, the transborder proceedings has been continued. We had a meeting with representatives of Estonia and Germany, regarded as one of the most difficult in Germany, bearing in mind the official role of nuclear energy in Germany, and as they have to sign an official protocol, but the meeting was completed. We've answered all their questions. And also, other than environmental proceedings, at the beginning of April, we've submitted an application to the Ministry of Climate and Environment to issue the key decision as the official position and approval of the government is that the project is in line with energy security of Poland, and it's a necessary milestone for all the next necessary permits. And as mentioned already, we are getting ready to next transborder meetings with Denmark and Austria. One will be at the end of May, the other one at the beginning of June. It won't be easy, but we are well prepared. Other than that, we are in touch with Polish Atomic Energy Agency. Last March, we asked for assessment of AP1000 reactors, how safe it is. So we work on different levels. As to the project design work, the middle item, at the moment work is ongoing to fulfill the pre-design agreement, but to give you more context how we've reached it, the key points over the last few months. Last November, the Council of Ministers adopted the resolution to build a large-scale nuclear power plants in Poland, and the first one will be built using American AP1000 technology. Then, last December, we as PEJ have concluded an agreement on cooperation with the supply of the technology, Westinghouse Electric Company, and at the end of last February we signed a bridging contract to the work preceding the design of these power plants. Let me clarify what it really means. And while talking about the bridge agreement and how we've reached it, generally speaking, we've analyzed all the key nuclear projects over the last 20 years to see what kind of mistakes or errors were made by contractors or others in order to avoid them. One of very often occurring one was that the investor wanted to enter the large contract having no finished design work of the reactor. That often led to a situation that what you had on paper could not be directly, simply built, and generated additional costs, jeopardized the schedule. There were delays and increased costs. We've all heard of it. So we decided to sub-stage the contracts into several smaller ones, so that in the process, together with the suppliers or the key main contractor, we could understand well the complexity and the readiness of the reactor to be built in our particular location. Hence the first agreement for pre-design work. Now we are negotiating next agreement for the design work and the conceptual work to build our reactor. So the project is at a higher stage. Then the third of the aspects, we undertake different activities in the relation to the adjacent infrastructure, which is necessary to build and to operate the power plant. While talking about the infrastructure, I mean several already mentioned projects such as energy infrastructure, high and low voltage grid, telecommunication or information infrastructure, transport infrastructure, road, rail or maritime routes necessary to transport several components necessary to build the reactor, and also water supply and sewage, waste management related technologies and other technologies like the premises or boarding for the employees. We are implementing these projects together with our partners. We have listed here like the General National Roads and Motorways Directorate. We're talking about made access road, railway project together with the Polish Polskie Linie Kolejowe, the maritime office in Gdynia, where we work about the depot, the MOLF marine offloading facility necessary to transport components, some very large components necessary for the reactor, and also Polish energy, grid energy. what's worth mentioning is that the projects are not only implemented for the construction of the nuclear power plant. Residents or tourists will be able to benefit from them in the region, so we can see more than just one specific objective. And moving to the major further steps we are undertaking as a company, so that the project be implemented. We have the key items we are preoccupied with right now, we are working on. 2023 is a key year for the project. Many things have already happened, as I've mentioned, although a lot of work is still ahead of us for the next quarter of this year. So within a few days or weeks, we plan to sign a tripartite agreement on cooperation with the technology supplier, Westinghouse, and the key main contractor, Bechtel. They work within a consortium, and we want to sign this agreement, and this will in fact approve the conditions of cooperation between us and the consortium, Westinghouse, as agreed. And we also monitor the process to obtain all the necessary permits. We are getting ready to talks with the Danes and Austrians. Within the next few weeks, we are waiting for the decision, key decisions on hookup. So these processes, administrative processes, are being implemented, and internally we develop IS skills, so that we reach the status, as it's called by the international smart intelligent customer, where we play a proactive role in the process instead of that of an observer. We want to develop these skills in different fields, including that of the operator, as soon as possible, so that we have all the skills and the body of knowledge at this very design stage. Then, as I've mentioned, we are negotiating a design agreement, the contract, yes, engineering service contract, precisely we want to sign in the third quarter of this year with the Westinghouse and Bechtel consortium to build the reactor in a specific location, and we continue close cooperation with local central administration, necessary entities to give these permits, like this Polish Atomic Agency and the supervisory office. We exchange knowledge and the status of work with them, so that the cooperation goes smoothly, continues smoothly. That would be it. While talking about my brief presentation, I hope I managed to present in a nutshell the status of our project and the key priorities and plans for the future. Although, should you have any additional questions, I'll do my best to answer them. Thank you very much for your attention. Ladies and gentlemen, should you be willing to ask your questions, please don't hesitate. I don't hear the gentleman. He's speaking off the microphone, but I think I've gathered what he meant. Thank you very much. Piotr, thank you very much for a very nice presentation. First of all, it's a great satisfaction to a professor to see former students who take over the organization.
W 2016 roku chyba gościłem w Oskarshamn delegację PGJ i gminy Choczewo. I po wizycie zapytałem wójta i ludzi stamtąd, czy ja państwa przekonałem do energetyki jądrowej. Oni powiedzieli: panie, pan przekonuj PGJ, niech nam powiedzą, ile zapłacą za nieruchomości i kiedy w końcu zaczną tą robotę. Więc pytanie numer 1. Czy zaczęliście już wykupywać nieruchomości w tamtym rejonie? A po drugie, powiedziałeś, że tu idzie ta współpraca OK, ale jakie są najtrudniejsze momenty we współpracy z lokalną społecznością?
Jeżeli chodzi o lokalizację, dziękuję bardzo za pytanie.
First of all, thank you very much for your question, and it's very nice to see you, Professor, here. As to the location of Lubiechowo-Kopalino, most of the land belongs to the state treasury. Although, yes, we are in the process of acquiring all the other necessary plots of land. As to your second question about the most difficult points, often we hear about the concerns of the local community, of the impact of the construction of the local infrastructure. Like, for example, the transport of all these components may have a negative impact on the roads structure. But as I presented, we work with the National Directorate of Polish Railway Authority. We want to build the infrastructure to improve it, not only for us and to carry all this, but also for the local community, and to make sure that we won't do any harm to the local infrastructure. So these are the elements that we have to clarify and that we present, and we're open to discuss them with the local communities so that we can persuade everyone on to present the plans, how we want to do it, and to make sure that they know that this is to the benefit and not to the detriment of the region. Thank you very much. I could see someone willing to ask the question at the end of the room. Is it question is still pending? Good morning. I have the following question. You have said a lot about the discussion about whether you select a French or American technology. I'm talking about the reactor. I have the question relating to the end of the fuel, so the nuclear waste management related one. Do we have agreement signed with the French concerns, companies that process the waste fuel, nuclear, to close the fuel cycle? Thank you very much for this question. As to the fuel cycle, it will consist of 3 items. In fact, after the end of the campaign, and the waste fuel is cooled for a few years in a basin, in a vessel, the building of the power plant. Then, for several dozen years, it's transported to the so-called disposal room, also within the premises of the plant. The waste is, of course, protected in the multi-layer system with the nuclear neutral gas, so that we meet all the standards. And only then, in a few dozen years, they will go to the deep landfill, let's say, to be the Polish waste management plan. As to specific contracts, it's too early to determine that, even though we are analyzing different long-term options with the central government administration for deep storage once we transfer this waste, nuclear waste. Anna Błażewicz-Stasiak is my name. Good morning. My question is, already you said about the readiness of the transport infrastructure in the region where the first power plant will be. We are part of this discussion and we are quite proactive. I represent the local authority, local government of the province, of the region. And I have a doubt, because the schedule showed by different entities, the moment to start the construction and the moment to start the preparatory work will not be the same as the readiness of the transport infrastructure. And we have justified doubts, I think, whether the existing infrastructure at the county or regional level, local level, will not be overloaded during the construction. We have different experiences with other strategic capital projects. Unfortunately, roads are very much degraded afterwards. And it's not always that the investor feels responsible to support and to participate in the cost of recreation, of replacement of this infrastructure. How do you perceive all that? Thank you very much for this question. It's a very justified question for the local residents in the region. As far as I know, we are in touch permanently with the representatives of the administration to develop a specific plan to determine it. And we're also in touch with, and we collaborate with other investors who want to build large projects in the energy sector in your region, who will also use similar routes. So our schedule and that of the adjacent infrastructure want to optimize by consulting you and to provide all the activities, all the funds necessary to minimize any adverse impact. But as I said, it's an ongoing process. So we are in touch with the administration, with the authorities. Piotr, thank you very much for these exhaustive answers. Piotr will be with us, so we'll have an opportunity during the coffee break or lunch break to talk to him, to discuss things. Now, to stick to the agenda, I would like to invite Robert Pakulski.
The theme of Polish power grid, which is Polskie Sieci Energetyczne in Polish, this being the name of the company, the consortium actually, has already reappeared across the presentations, the recent one included. Now Robert Paprocki is kindly asked to dwell on it in more detail with regards to cooperation of an MPP with the electric engineering system, power system in brief, under the umbrella of Polish Power Grid, PSE. That's the Polish abbreviation of and a circular name of the company. I am basically a plenipotentiary of PSE's managing board for integration of NPPs within Poland, and integration is not a question of connection only, but it relates to the operation and work of the NPP within the system. And that's the key point to my presentation, which may already function as a summary, really. Okay, let me briefly report now on the subject described as integration of NPPs. From the system point of view, or system-wise, NPPs are quite similar to the other power plants, like conventional plants, CHPs, starting from unit transformer, turbine before then, steam turbine, whatever else. What differs NPP from the others is the source of thermal energy, the source of heat being the energy, ultimately being the reactor rather than a boiler, for instance, or furnace or whatever, which also relates or translates to its cooperation, to its integration within the grid system, the power system. We all can see that potential threats regarding breakdowns, failures are much more far-fetched, much more complex, and so on, as compared to boiler breakdown, for instance. As we go through the subsequent slides, we'll see in more detail what I mean by that. So not only normal, ordinary operation aspect is included, well, intuitively we all feel and know that basically that we have to have control over the chain reaction, over the operation of a reactor, of any reactor, in the context of supplying one's our needs and so on and so forth. But it also relates to shutdowns, decommissioning, and anything involved in it. In these aspects, with relation to these aspects, an NPP is kind of unique. That's why the essential specificity or uniqueness of an NPP system-wise. Secondly, usually an NPP is the largest element or unit, if you prefer, within a system. As any large unit, be it coal-fired, be it nuclear, this does translate in an essential way, in a number of essential ways, to the work, to the operation of the system. Okay, let me show you a context of connections with the other systems. So integration works also on the level of involvement of the other blocks, of the other units. Here, the blue area recently expanded to Ukraine and Moldova, basically from March last year, because of the war situation in that region. So the war has accelerated things. Back to the point, power grids, power systems are not only interconnected within the continental Europe, but also overseas, far away overseas. As we expand a system, it is all the easier to ensure the safety and security of its operation and provide for mutual help, assistance between the systems and the reserves, and to potentially use the reserves and provide for them. For these reasons, as from mid-20th century, such connections have been established. 70 years ago or more, such an integration process started. Monopolies were the case, especially in the former communist Europe. Today we have a free market system, which translates in a variety of ways into the way large production or large generation units operates. So there's quite a history, decades of history behind the business. As far as the EU member states are concerned, the guiding, the prevailing law is the EU law. This is mainly reflected in the blue area on our map, as well as the red one regarding Scandinavian countries or northern countries. There are interconnections between the two areas. I am a member of one of the system integration associations, by the way. Decades ago, the cooperation was voluntary. National power disposal bodies or power distribution bodies, whatever the exact English translation, were the case decades ago. Today, specialized officers in charge. As regards the peak demand, it is 27 gigawatts installed capacity of the sources, at the level of sources, 60 gigawatts, and the annual consumption is defined at 173 terawatt hours. That regards the national power system. The KSE in my presentation stands for the National Electric Grid and Power System. The largest units within the system are basically nuclear ones, especially in France, like 4 such units of 1,500 megawatt each that can serve as a reference incident. Those are the largest within Europe generation units. This is not of a huge challenge just because of the integration factor. In practice, the continental ways of methods of regulating the powers, balancing powers, including a variety of incidents which do happen, allow for a margin of safety at the level of hundreds of megawatts, especially in France with a strong nuclear system. Parallel shutdowns may take place, but regardless of all that, even up to 3,000 megawatts, the margin of safety may allow for as much as 3,000 megawatts. So I can refer now to the Scandinavian system, which is roughly six times smaller than the continental system, core European system. The most recently commissioned reactor was started up weeks ago in Finland, in Olkiluoto, the one that has been constructed and commissioned for almost ages recently. And it is immediately integrated into the region's units and systems and grids. An automation system has been started up there, which switches down immediately 300 megawatts without any effect on the operation of the whole system. So another safety margin, if you like. Oskarshamn, if I'm not mistaken, in Sweden, is probably within that grouping that I'm referring to now, is the largest nuclear unit. So commissioning of a 1,600 megawatts reactor in Finland has not really has not really impacted the operation of the whole system regionally and Europe-wise. This chart shows you historical development of generation or production capacities on the scale of Europe and worldwide, really, with coal monoculture having been predominant for ages. Here you can see solar, wind, photovoltaic, being replacement of solar, renewables having seen an impressive development and evolution in the many recent years, dozen or so years recently, about 2 decades roughly already. Obviously, it's based on the natural phenomena when it comes to renewables, but such basics are quite well known to you. NPPs are designed to, in the coming decade, to replace the coal-based sources, baseload ones that are due to be decommissioned gradually. In the area concerned, what I mean by baseload is the part of the load of the system, if you like, which does not change over the year or alter over the year. We know, obviously, that the use is different day by day, really, month by month. That's why my graph, my chart here, depicting the demand, the minimum demand and maximum demand nationally for the last year, 2022. The 2 days of minimum and maximum demand being the red line and the, well, navy blue one, respectively. 25 plus megawatts, being maximum 10 days later, all within December 22. The second day of Christmas, which in English terms is the Boxing Day, name it as you will. Probably quite a warm day given winter conditions, the winter average. That's why the demand went down, even with respect to some maximum, a minimum summertime demand rates. Very interestingly. So, a classical winter day, not too frosty, as I said. So between December 16th and 26th last year, with a roughly warm winter at that time. Not yet January or February this year, because then it's changed. Then it changed. To the right, on the top graph, you can see how roughly the demand was covered, the reserves were used at the minimum level, the minimum necessary reserves, and their use and their consumption. The minimum demand was 19 gigawatts. So the minimum demand of 10 days later made a difference. So the minimum, given the system, altogether is 12 gigawatts plus 12 plus gigawatts. Night time, basically. So the coverage of the demand was done, was carried out, used to be supplied basically by coal in the good old times of coal monoculture, whereas single peaks were covered by hydro, among other things, hydro pumping stations. Why cannot we see a peak there in the graph? Well, a room had to be provided for yet another night time. that particular point of the 26th of December was specific enough. It was rather windy. There was a rather windy day, I mean, and cogeneration required extraordinary means to be employed before some of the units were shut down. The operator of the grid system did their best to minimize the volume of the wind sources, and therefore they worked on a flat basis rather than with extremely clear peaks. We do not have such sources regarding hydro as they do have in the Alps or other like areas. But we managed, obviously. This is just giving an example of last year, December last year. Yet another drawing system power plants of various sorts, like gas, water, lignite-powered, coal-fired. The wind ones are mainly located in the north of Poland. Photovoltaics is scattered more or less across the country, evenly, roughly evenly, in a couple of coal units have been integrated into the system in the recent months without any problems, really, because we operate within a large synchronic area, as I said before. And as I showed you, within the last decade or so, we have integrated a couple of photovoltaic and wind sources, uncontrollable ones, and this came as a real challenge. The integration of them required quite an effort apart, but we managed, in fact. All in all, there are two NPPs, Kozienice and Bełchatów, the latter one being lignite operated and the previous one being coal operated, whose installed capacities exceed 1,000 megawatts. As regards transfer grid, at the background, shown at the background in the previous slide, this nowadays looks like that, from sources to consumers. That's why the density more intense in the south of the country, traditionally, because we have availability of the sources, deposits and whatnot. And in the winter days, referring to wind energy, renewable energy, you can see less density of the grid in the northern part of Poland, because of the wind energy complements it for the balance. In windless days, well, we deal with the kind of changeability. This has been historically established, really, of the recent 2 decades, 1 decade especially. We have to meet the challenge of uncontrollable sources, a challenge of retaining a balance within the system and complement its elements one for the other. Market actors have their good reasons, each of them, to work in a variety of ways, flexibly, rather than in a very much established and stable way, as was the case still 20 years ago or so. The connection between the systems, the interconnections, caused that traditionally west to south, and fortunately recently north to south flows have been observable, have been the case. Not really from the east, fortunately, especially in recent time. Here is the deployment of the transfer grid, and as well as planned within this year, at least by the end of this year. This is in accordance with the development plan established in November 22. Such plans are every so often, each 3 years, or even formally each 3 years. But in practice, even more frequently than that, updated and amended because of a dynamic developmental phase that we are all experiencing these days. Changes in the environment and the circumstances are so much faster than they used to be that, well, increases of capacities are more dynamic, are now being faster, and we have to match up with such fast developments, faster and faster ones. Not to mention a long-term process of gaining all sorts of permits for, deploying structures of various sorts in each particular parcel of land. But that's a separate story. As you can see, the assumptions for development of uncontrollable sources includes basically the installed capacity of roughly 20 gigawatts in PV, 14 for onshore wind, and 11 gigawatts for offshore wind. So we can expect intense development of transfer capacities from the north to the south, and obviously once the NPP is sited in Lubiatowa Kopalina, which is north of Poland, very close to the seashore, this will be made part of the picture, so the power will be taken out systemically for the Lubiatowa siting into 3 other close units. It's a matter of the years to come, a dozen or so years to come. This is shown in a more detailed manner. Because of lack of time, let me, however, pass on to further part of my presentation. If you're interested, we can always get back to any of those slides or talk on private to those. I'm addressing those interested. As to systemic analyzers for new production of new generation units, so-called N1 criterion says that after the commissioning of a single KSE systemic element, the parameters of the remainder ones within the permitted limits have to be observed, and within a quarter of an hour the operator is bound to re-establish the fulfillment of the N1 criterion. So I'm accelerating a little bit, so as not to slip out of the time frame. Let me show you more aspects of the specificities of the NPPs. It is so important to observe this specificity and uniqueness because of the necessity of driving out the decay heat in breakdown situations, in failure situations. So there's a variety of scenarios drafted for the purpose, well, compiled, I should have said. Such situations do have an effect on gross, the potentiality of gross breakdowns, including core melting, God forbid. So a redundance of NPP's own needs as they are supplied have to take place in the very basic system from the transformer of their own units needs and as a reserve from at least one reserve transformer connected to the system. In case either of these sources fails, the nuclear unit is supposed to switch into working to fulfill its own needs, to put it more colloquially maybe, and if this process includes a variety of transient stages, this might fail again, and in such a case, what is needed is powering, supply, feeding the safety systems and security systems for the purposes of the NPP from the outside batteries, from the diesel generators, gas turbines, and assembled batteries, which are all so redundant. So there is a whole system, a whole network, if you like, of redundancies or layers of redundancies. So in case of a gross blackout of the system, of a large part of the system at least, part of which being the NPP concerned, so based on all the previous considerations, it follows that NPP is the highest priority, top priority unit or element with regards to re-establishing the power, the voltage. So systemically speaking, well, its role is one of definite priority. So within 2 or 3 years, an NPP should become operational again, fully, or at least fully basically, this is what I mean. So this is, in rough terms, what is so specific about an MPP. So all sorts of things are the case with regards to redundancies, for such redundancies to be provided for safety and security of lines that let out the powers, bits and pieces of power up to the required quality and cyber safety. All this has to be provided for. All this has to be ensured. All these aspects, and obviously the redundancies between the operator, the NPP, and the operator of the transfer system. This is the very last slide. So I'm still roughly within my time frame, which summarizes what I've said so far. This breaks down the NPP's characteristics as versus the system. So it is well, a controllable source, working whatever the consumers, the users and users would like to have it operational, so regardless of the weather condition and so on. Possibility of load following is provided, very importantly, but well, high level of predictability of the schedule of its operation is a very important thing. So all sorts of planned shutdowns, like for the purpose of fuel replacements, those can be designed or scheduled a couple of years in advance. This is of a critical importance for the operation of the system, really, and large period between fuel campaigns of more than 12 months is quite a demanding characteristics, because this allows to to collect the fuel reserve for the NPP for a period of a couple of years, and the 60 years period of operation as presently provided for, plus an extra 12 years, so almost 100 years really, giving us a sort of peace of mind, which is very much valuable, equality. How about those uncontrollable sources? Some of you might think, what happens if there's an excess of power within the system? How the new systems have this load following capacities, new technologies have it as an like an ordinary factor, okay, or characteristics, in line with the push-away capacity. Sometimes, you know, the minimum startup period and minimum shutdown periods may differ. But regardless, this aspect, the baseload operation is at least provided for, thus allowing for the balancing of the system, stability of the system. Well, I have skipped slightly over the specificities of certain technicalities, but let me only mention that an NPP, as is the case with any other conventional power plant, it provides inertian short circuit power or capacity into the system, as well as passive power into the system, which is really quite beneficial thing, quite beneficial factor with respect to the grid, with respect to the system. And development of the nuclear in general is means entering a different level of culture, of safety and security, of technology. Well, redundancies, the ones that I've summarized to you, are of a challenge, yes, but all in all, to sum up, NPPs are friendly, is a friendly solution from the standpoint of the system. Thank you very much indeed. Thank you very much for this presentation. One quick question, if anything. The lady over there. Please fetch the mic to the lady. Just one quick question so that we can pass on to the last presentation of this morning series. Be brief, please. Dear lady, Weronika Zapaśnik. As far as the preparation of the infrastructure is concerned, I've looked on the map. There is now 110 line, which is to supply, to feed the construction site. According to GPZ, it's going to be 400 kV. There are going to be so many cranes. It is rather a detailed question. Yes, it is. I didn't want to enter very much, drill down into details, but the general plan is that the construction site will be supplied from the 220 kilovolt lines. So it's going to work on both sides, from both sides, and as a target on the operational level, once commissioned and so on, the potential the redundancies will be also allowed because of that. So this was part of the assumptions that were made without the detailed design being put in place yet, but it looks like it is going to be to cover the needs. And if still insufficient or inefficient, definitely it will be efficient and sufficient for the purpose of the construction process. But if not, later on, this will be re-implemented, redesigned, and reconstructed if necessary and as long as and as far as necessary. From the standpoint of the redundancies and working for the unit's one's needs, the such demands are, as versus to the other classical technologies, are really very much to the point, so to speak, and are really controllable and deliverable. So there's no worry that something might unexpected might happen. I hope I've answered your question. Is there any concept? Thank you very much. Is there any concept for the route through the lands concerned as regards to siting? The 120 line, there are 2 lines to be provided. One of those will be owned by the distribution system operator. Partly, they are going to be constructed by the investor. So it is a kind of cooperation between all those entities involved with regards to the power supply and connection process. Details of it might be verified at the stage of talks with the specific supplier of the technologies, and small amendments can be made to this end. Thank you very much indeed. Now, Robert will be available to you. We're slightly out of schedule right now, so let me invite the last of our speakers in this session, Adam Rajewski, Vice President of the Board of the Nuclear PL Foundation.
Thank you very much. Let me answer your first question. It's a simple question. I'm a graduate and researcher part-time at the Mechanical and Aviation Department of the Warsaw University of Technology. I'm Deputy President of the Foundation, and I also work for Polish Polymers Mostostal company construction as an expert for nuclear project, and also one developing others while nuclear ones are not present yet. I would like to combine several themes and just a few days, how to make it to be colloquial, to have a nice power plant, not only the slides, and to generate power and to supply it. In Poland, we have lots of presentation plans about nuclear energy, some more realistic, some less, some more advanced, some only on paper. And there are also some, unfortunately, like cabaret ones, that in 2 years I'm not name this technology. I don't want to have a nuclear power plant. So I would like to make a reality check. There is no Polish term. It's an English term, reality check. What to do to build a nuclear power plant? We're talking about nuclear power plant as something specific. Before the coffee break, just asking this question, what's the difference between a Sparrow? It's a kindergarten. Well, what makes a nuclear power plant different? Left-hand side, is it a nuclear power plant? Or maybe that on the right-hand side, who thinks? No, all the others don't have an opinion. On the left-hand, former German criminal, on the right-hand side, conventional one. No, architecture-wise, they not that different. But it really matters. A nuclear power plant is simply a large power plant. It doesn't differ that much in the construction process. If you look at the zoning plan from the environmental impact report. You can see the buildings housing the reactors, fuel storage tanks. This is what makes it different. These are built slightly differently using different technologies. You need specific steel structures. All the rest is like in the conventional power plant. Of course, different parameters for the steam, lower, easier. Other than that, you just build it similarly. The difference, well, let's take a look at the site, at the construction site in the US. Fourth will be a Model 1 for Lubiatowo Kopalin. And that's it. All the rest of this, it's a large construction, industrial construction site. The difference is, and fundamental one, as compared to conventional, is about the number and type of documentation. You have to process at different stages of implementation. It will torment everyone who would like to, or haunt everyone who would like to build it, and especially those who are going to actually build the. How many times you had problems with approvals of projects, with approvals of their components, and so on and so forth? I don't want to point to the names of the projects we all know. Well, in fact, you can always, blame everyone. There's no risk that both Koreans, Americans had a problem while commissioning, for example, launching. Thousands of documents were missing. The French and the Germans had problems, not only once that things did, and the construction process was stopped. It's not a funny story, not a funny topic. If things are not in agreement, the best bad headlines in the press, that's still negligible, but halt on the construction or operation is worse. Well, the security people, or that's the Ukrainian example. They come and they say stop. These are things thanks to which such construction is difficult. Talking about this scale, there is no easy construction, but let's get back to the very process of the construction. It's part of the information card at random almost. One of the newest nuclear power plants in Europe, from International Atomic Agency. Different dates, start of construction, completion of the construction, and they are divergent. What do they mean? Often we have to answer the question as the country says, how many years, how long does it take to build such a power plant? The contractors suppliers would say 3 or 4 years only. It varies. But the basic question is, from when to when we measure the construction process? There is no one ISO standard answer. Let's look at all the processes that, the length, you can find it in the web, of all those built until recently, all the units globally. It varies. In this case, it was measured from the first nuclear concrete to the synchronization of the system with the grid. As you know, I think neither the first grid nor the synchronization are the first and the last step. If you look strictly at the construction process to internal dates, the process of the construction, the nuclear part, it can be limited to this. The first nuclear concrete, so the first armed concrete pertaining to the nuclear security, the foundation slab, and then the end of the construction. It's all built, it's there. All that was to be filtered, assembled, is there. It's the date that's shown by the suppliers, technology suppliers. But, as I said, there's no beginning and no end here. That's the process. It looks like many cranes, a lot of concrete, lot of structures. I'm not going to expand very much on that. But then you have to launch, you have to commission this installation. The date, which is a very important date, where you can open a bottle of champagne. There are more such dates. So the first criticality of the reactor. But before that, the reactor has to go through different tests of cold and warm launch, that nothing is leaking, literally, that automated systems work, that the reactor. Well, you have to load the fuel in the meantime. You need an approval for that. And then once it operates according to the plan, you can synchronize the unit with the electric energy system. So you switch and you give the power to the system. It's not the end, even though many present it as the end, and they want to show that it's a quicker, shorter process. But the power plant, yes, they can generate energy to the grid, but there are tests in between in order to prove that it will operate properly, it will change the power. It will meet all the requirements for the grid. It will be hooked up to the grid. So it's a long process. And finally, we reach what is the end of the construction process, and that's the commissioning of the unit to the plant operation, start of commercial operation. And only then we have a ready nuclear power plant. From the end of the construction till this months or years may elapse, the test and confirmation that it meets all the requirements of the electric and also that of the investor. There is a contract saying that the power plant has to have certain efficiencies, that you have to measure, a specialist company has to do it. All that takes time. So, in the best of scenarios, it's about 6 months, but it can be even longer between the end, especially if things don't go very well. We know problems, not only in nuclear energy cases where it would take years. An example I've shown earlier, the problem with the turbo unit. In France, in Japan, it happened also. If according to the plan, it means many, many months of work of a team of specialists. Let's look at the beginning. The first nuclear concrete is not the beginning of the construction process. You have to dig a hole, you have to put the rods, and it takes time. But in fact, before the beginning of the construction, lots of works on the construction site are taken, preparatory work. And it's a lot of work for the builders with laying concrete, erecting the building, construction, the structure, providing power to the construction site. It's a separate story, not trivial, especially if it's a remote site. The power that you usually don't need in such a location. You have to build transport infrastructure as well. All that may take time. So when the first contract is late, it's Hinkley Point picture. From the layman's perspective, it's, you've had the construction site operating for a long time. People digging, building for many months or years even. That's one of the newest construction sites in China. From the perspective of logic, it's hard to be called the beginning of the construction. It's a very important stage from which you begin to count, but it's not the beginning of the construction. It was way before, a dozen months earlier. That was quick. Now it's something like the hunky-kiwi. Not anymore, as Finland was investor, but in fact Finland as a state said thank you to the contractor, and they sent them wherever. But the preparatory work to build the power plant started in 2016. Of course, there were many delays in the design work. So in 2016, they started preparatory work. The first concrete was to be laid maybe in 2022, not at the beginning of the year. So it may take a few years. That's the construction site when the decision was taken to discontinue the construction. Buildings, administration, and so on. It was leveled, deforested, and a harbor port was built. Often you have to build provisionally port, because all the toys you have to bring to the construction site do not fit into inland transport. They are too heavy, too big. So if you think modular small reactors are easier, in most of the cases they are not. Diameters may be smaller, but pressure vessels are big anyway, so they will be bigger than the railway gauge will be not wide enough for them, or the room under the bridges. So a promising picture from the US, let's say, when it was transported by rail. In the state it's feasible, because I don't remember, it was a prairie or something like that, but American Railway Authority, well, that was the feature. It was not electrified. So in this particular case, it could be transported. In Poland, it would be not possible. The diameter is over 4 meters of such and the gauge is 3,100 plus millimeters. So I have to build the infrastructure, you have to supply the construction site, I have to build before the first nuclear concrete is laid. In order to start with the construction, you need a building permit. You need, I don't refer to specific documents of Polish regulatory order, not quoting the names, it could be for another and much longer lecture, but also you need the permit, not only in Poland, of course, there may be separate permits for preparatory work and the construction itself, need other permits, and well, by the governors, and they technically they are interdependent, but these are separate processes. In order to obtain that, you need to get it ready. You can get part for preparatory. In some cases, you have to design it. Designing a nuclear power plant is not a trivial thing. A multi-sectoral project is an issue to be tackled by, at least partly by Polish team. Even if we buy a reactor standard off the shelf in the US or Canada, we can just copy and paste it. Of course, certain components, certain elements, depending on the agreements, can be transferred, especially if you talk about the reactor island, but in case of conventional island, not necessarily, and auxiliary adjacent things has to be designed from scratch, depending on the particular location. Like in a case of contractors, you not only need time to design, it's many months of work of a multi-field team, but as you may have more projects, we can run across the risk that you won't have enough people to design all that during the same period of time. and the implications may be difficult. As you probably know, in Poland we used to have more, but now we have very few design of bureaus, no matter what kind of plant we are talking about. We don't have a team to design nuclear power plant. The teams that can do it for a big unit in a conventional power plant, that too maybe. That's all. So this will not be simple. But before we start the designing process, some other process may overlap, some may not. You have to prepare the process already mentioned, and that's the environmental impact assessment. You have to examine how it will influence you have to get a decision together with the transborder consultation stage. Developing a report takes rather years than months. The procedure of decision issuance, we'll see. In case of the first power plant, probably we won't be able to do it within 1 year. So the bottom line is that even if the construction itself, from the first concrete to steel and the end, could take, let's say, 3-4 years, although 3 is doubtful, we have a lot of different works that require many years, both on the left and the right-hand side of the process pictured here. So these are things obvious, but we must not forget about them. So if we dream that we have these power plants quickly, it won't be true. And our program is criticized by the public very often and very much due to its not very energetic implementation over many years, but probably it's not difficult to say that since 2012 it started accelerating, but things were happening. The PEJ company on the left-hand side here, but it doesn't mean that nothing has happened. There's a location assessment, so the pre-checking of location, whether it's fit for a nuclear facility. It means also years sometimes of work, and that also means that new projects being proposed are 3 or 4 years from, well, to what extent the General Director of Environmental Protection be overwhelmed with all this paperwork, and Atomic Energy Agency as well. And even in conventional energy sector, it's hard to obtain environmental decision in due time. Some have waited 9 months longer than theoretically. Well, you can complain, but well, to the administrative court, but then you will even extend the process in time. So being enthusiastic that nuclear units can be created in Poland soon in other projects which are already retarded may be premature. You need to pre-select location before the examination. It means work as well, like that performed by the OSGE as investor presenting first location. Of course, it was a result of an analytic work already done. You have to make agreement with the operators, because if you have a relatively close plant, reactors or powers, it cannot be done. And it can be like if we look at the map, if you look at the grid, for example, read the plan for the development of energy brick near Pątnów, where there is a location. They plan the new transport lines in the grid to get the justification is that it's to get the power generated by Lubiatowo-Kopalino. There are other processes, not always critical path. Selection of suppliers and contractors, you may think that it's been done. So every investor has a partner selected by themselves or by the government, depending on the project. We've done it. Not always. The Czechs have competitive bidding. Negotiation of the contract. For example, we have companies that want to sell, the companies that want to buy. It's very simple to sign a contract. No, it may be not so trivial, bearing in mind the nature of each project. We talk about conventional power plant with the whole time horizon of 4 or 5 years, usually 4 years. It's problematic due to non-stable market. To determining the price, the cost within 4 years is not a trivial matter, raising more and more problems. And here we talk about time horizons which are different. We talk about the implementation of the project which is to be completed, say, in case of Lubiatowo-Kopalino, in mid-30s. Not talking about 3 units. So negotiating such agreements is very serious, and there are no good examples. There were model agreements securing the interest of the investor, Vogel or Polchwotów. In one case, the contractor filed for bankruptcy, and in the second case, they didn't because the state bailed them out, but it ended very bad. So such an agreement is so there are no good models, no good examples. As when in the Western market world, an independent supplier will agree with investment, will sign an agreement for comprehensive construction. I'm not counting some British things that were French. It's the French state purchasing from the French state. The business model determination, how it's to operate in the energy market. European market is not a friendly one today to long projects with long ROI and getting the funding. All these things take time. By the end of the day, what seems to be like 4 or 5 years to build a power plant, it may take even 10 years, not because someone is doing nothing and that the politicians do nothing and only take high salaries, but there are lots of processes that are largely, let's say, well, back in the back office, going in. And these take a lot of time. So that means that a few years, especially in new projects, you won't just announce a decision today and by the end of the year first work in the site will start. So, if we talk about this schedule, PPJ has a 15 years horizon for one plant, 20 years for both, plus delays, if we talk about this scale, as geopolitical situation or conditions are as they are. Finally, a humorous cartoon I just came across yesterday on LinkedIn. From presentation to the implementation. So if you look, especially for new construction of reactors, nice visualization, but it's one of the better if there is a cooling system, at least in some it looks like a shopping mall. When it goes through the sieve of the designers, it looks not that great, but the last one, as compared to the first one, has the advantage that it probably will be in steel and concrete, and it will be built. And I wish that to myself and to you, ladies and gentlemen. Adam, thank you very much for this presentation. I would like to thank all the previous speakers. I think Adam has managed to provoke us intellectually to discussions. So now we'll have a coffee or tea break, and we get back, resume at 5 minutes past 12. Thank you very much for your attention, ladies and gentlemen.
Halo, tak. Witam Państwa po przerwie. Uprzejmie proszę o zajmowanie miejsc. Ponieważ moi poprzednicy mówili mniej więcej o swoim backgroundzie, ja chciałem wspomnieć, że jestem pierwszym absolwentem sekcji energetyki jądrowej, jaki uzyskał dyplom w Polsce na Politechnice Warszawskiej na Wydziale
at the Faculty of the Mechanics and Electronics of the University of Technology in Warsaw. I was the first graduate, and I'm going to lead you through the, ladies and gentlemen, of this session. We start from 3 presentations by the 3 major organizations providing and supplying power reactors worldwide. The first one to go is Westinghouse, the constructor and designer of AP1000. The second one, KHNP, the provider, supplier, designer, etc. of AP1400, and thirdly, EDF of France, famous for its great reactors, recently propagating their state-of-the-art reactors, which will be covered in more detail during the presentation. Mirosław Kowalik, President of the Board of Westinghouse Poland, in charge of investments and investment projects for NPPs, including within Poland, basically within Poland, based on the proven AP1000 technology. Mr. Kowalik has graduated from the Electric Engineering Department of the Akademia Morska, and he chaired recently Enea, one of the major power companies in Poland. We have a limited time at our disposal, and I'll show my dear speakers a card saying 5 minutes, just to signal to them that they are about to finish, should be about to finish. Thank you very much indeed. Good afternoon, ladies and gentlemen. Thank you very much, Professor, for this brief introduction. Already 5 minutes of delay, but hopefully the material I'm going to present to you, which I'm going to summarize to you in its entirety, more or less, will be beneficial. The last presentation was not overly optimistic, mind you. Let me just add that Poland is capable of dealing with facing the challenges presented by our last speaker before me, but safe and secure construction and operation is the key to success. This is the major point, and all in all, a conclusion already of my presentation. Okay, Westinghouse is a world-recognized company to you. We've been through a variety of stories, of vicissitudes, that's what I mean. One of the largest conglomerates to ABB right after the fall of communism in the early 90s. So I was part of ABB at that time. Quite records with nuclear as far as my career is concerned. But this is a side remark. The nuclear market, energy markets, in specific nuclear energy markets, something very well known to me in Poland and its region. Westinghouse in mid-90s offered upgrades of our standard product, which is 200 megawatt turbines, which are becoming obsolete these days gradually, and nuclear is going to meet instead the climate goals, which is climate neutrality by 2050. That's why Westinghouse, that's why our position, that's why the huge perspective that we've developed and try to expand for ourselves, for the others. And nuclear investments, nuclear projects are thus enabled to the best of our abilities, and certain of our actions include gradual replacement of emission sources by emissionless or non-emission sources, which is interrelated with cogeneration variety of areas. And nuclear is the answer. As far as Westinghouse itself is concerned, maybe you've seen a film, a video regarding the dispute on electricity, as well as whereas it's supposed to be based on AC or DC. As Westinghouse joined the dispute, this being critical process in the construction of an MPP. Westinghouse, together with Nikola Tesla, in the meantime, so they have joined, and well, alternating current world, if you like, has been managed. This area has been well managed by Westinghouse. There is the know-how aspect to it, human resources, manpower, all this being quite of importance really. Added to what I've said before, as regards Westinghouse itself, more than 50% of the present-day fleet, over 440 reactors operational worldwide at the moment, have more than 100,000 megawatts of installed capacity, the average being 400 plus per each. Just to remark to you, the year 1957, the first reactor, pressurized water reactor for the American Navy, was constructed by Westinghouse. That's the tradition, that's the history behind it, that's the know-how which is present across the company. An export of the technologies provided by us, designed by our company, exports towards Europe have been the case in the recent years, including to France. So part of French technologies are Westinghouse based and elsewhere. So tradition, knowledge and experience is what supports us, is what is behind us and our offer. Over 14,000 employees worldwide, with locations in a total of 15 countries, with a multiplicity of business lines, more than 70 facilities worldwide again, with a variety of functions implemented and operational, with access to more than 50% of reactor technologies operational these days, producing altogether a considerable amount of energy, 2,800 kilowatt-hours, if I'm not mistaken. 50 from Poland itself, so we can figure out. As regards the global footprint of Westinghouse, namely, let me just draw your attention to three elements on this slide. Fuel fabrication facilities located in Sweden, in the United States, and in the UK. As to the other things, well, take a look. We cover the entire value chain for the power sector, power engineering sector, nuclear in specific. starting from new construction projects, AP1000 being our standard reactor, through to innovation and development of Vinci, a macro reactor of 5 megawatts only, SMRs that have made a debut very recently on the 4th of May in Atlanta, US. So Westinghouse has resumed this particular product very recently. There is a division dedicated for operational maintenance. So once the NPP is started, is commissioned, we offer our customer an added value to optimize capacity and capacity factor of this NPP. As a rule, NPPs operates based on the base load, on their base loads, if you like, in order to be exploited, operated as economically as possible, rather than operating on the peaks. We quite naturally we operate within a balanced environment, balanced grids, balanced networks. There is a capacity to go much above it, but this should not normally be made use of or taken advantage of. Slovenia has recently got a permit from us for yet another 10-year period of operation. In the US, a number of reactors have been permitted as well by the surveillance, by the oversight office or authorities. Westinghouse is quite helpful in this respect towards its customers, clients, and the decommissioning area, something that we very much take part in, winding up, closing down of the NPP and bringing the site, the location, the sizing to their right conditions, so to put it. So this is where we are competent and offer these competencies to our clients. Our portfolio in terms of nuclear includes, once again, the standard product, our standard product, AP1000. This is going to, one section is going to be implemented for the first location in Poland, 1,100 megawatts, possibly even more, given the cooling conditions provided by the area close to the Baltic Sea. As a micro reactor, if you prefer, of 300 megawatts. We are working now on the generation 4 reactors, whose impact, whose environmental effect or impact is even lesser than that on the others. Polyformization, or whatever the term is a very recent solution enabled by this particular design, and well, lithium batteries based products are comparable on water storage, water tanks, based on a very different rule, based on proven technology. So, nuclear generated energy can lead to generation of hydrogen, which can be used for isotopes in medicine, which can be used in thermal for thermal purposes, including heating, even including district heating. a whole variety, a whole array of users, really. We are working on new products. AP1000 is our flag product, our benchmark product. In operation in China since 2018, in the United States, a couple of them. One of them has hit its criticality, undergoing control tests, and in the weeks to come, it is going to be made fully operational. Very briefly, the pictures, portfolio snapshots, our global products like nuclear fuel and others, available to you if you're more interested later on. Outside of the frame of this presentation, we provide a variety of fuels, of nuclear fuel types, including for BWRs, VVER and AGR. Especially given the present-day geopolitical situation, we have re-established ourselves as a reliable partner for Poland. Also, not far away from here in Sweden, we have a nuclear fuel factory. So I've mentioned the types of reactors. Well, PWRs come first in terms of our potential fuel capacities, but we are fully capable of replacing fuels from Russia, which had been supplying units in this part of Europe, Central Eastern Europe. So that covers VVER, that partly covers BWRs. Advanced gas reactors, AGRs, are definitely included. So this all stays within our array. This all, simply put, is part of our offer. As regards the nuclear island, we have a whole set of competencies as regards ordering, commissioning of components, of parts for the vessels, for the coolant pumps, for the steam generators, for full handling, for loading equipment. Also critical parts are parts of our offer, and nuclear steam supply system. Certain terms are not really equal in terms of finding good equivalence in Polish versus English. English has become the standard language, and to ease our communication, we use English, and on the other hand, we try our best to develop good Polish equivalents and equivalents in other languages too. This is a side remark. As far as engineering services are concerned, we are basically focused on enhancing plant safety, improving plant performance and reliability, as well as extending plant life. This is all offered to our customers. As I said, we have technologies, we have the documentation, and access to more than 50% of reactors operational worldwide. Automation, instrumentation, electricity, devices, appliances, whatever needed for the purpose, all part of our portfolio. We are capable of providing appropriate training to our customers. As you see, there's a list of functions for products and services reflecting our offer. Basically, cybersecurity is quite important to this end. IDT, very importantly for the operation of an MPP. very important. And the automation instrumentation systems, as you very well know, based on your experience, or at least theory. You might be familiar with the so-called Asian system. It now appears under a different name, but is all based on the Westinghouse know-how. Field services, implant modifications. This is all based on operational maintenance of the existing units in order to, as economically as possible, operate and manage those units, possibly reducing all that to the base load and base load related capacities, thus providing technical technological satisfaction. There's no shortcut, however. Reduction doesn't mean shortcut. There's bureaucracy around it, every so often based on our need for and everyone else's need for safe and secure operational NPP. So everyone would endorse it, I think, in every such respect, in every such case. Supply chain, including appropriate and adequate quality systems, technical norms, technical standards being observed, safe supply, safe operation, technology as per budget, streamline the location and siting to the conditions as appropriate possible, as adequate as possible. So the end product, after the burn-up of the fuel, is readily prepared well before then for decommissioning, for shutting down and ultimately decommissioning. We provide customers with various criticality points and modes of operation, wherever it comes to breakdowns or failures. We provide assistance. Some of the solutions are inbuilt, some of them are provided along the lines of the actual need. So if need be, just showing you bits and pieces of AP1000. It is a third-generation reactor, one of the most efficient worldwide presently. 4 units operational these days in China with a great capacity factors of around 90%, which is a record-breaking rate, really, in the sector, given the average sector's capacities. It is a proven technology, well-established one, and it is a technology that has been recognized by a number of regulatory offices, and it is up to the norms and standards observable and enforced worldwide. The technology was meant to design, the idea was to design a technology as reliable, as resilient as possible, as much protected as possible against any accidents and so on and so forth. This has involved a great investment and a great effort from the institutions concerned, licensing authorities, those that enable for commercializing the project. All the safety security elements of the reactor has been tested, also for unforeseen events or incidents. on a long-term basis. This calls for respect, and this calls for an afterthought. More analysis will be needed, perhaps, to see whether this type of reactor is capable of operating for 30 years and more without an environmental impact. We would like to avoid problems like those that appeared in Fukushima due to natural factors, as very well know. So that's for the American regulator certified our AP back in the year 2016. Safe, simple and standard. This is what it is as certified. As compared to AP 600 and other systems, Westinghouse engineers have set as a goal for themselves to reduce certain elements which relate to its to the solution's reliability. 30%, 35% reduction in pipeline, about 40% reduction of pipelines, 80% reduction of control cables, and so on and so forth. A huge, enormous effort of our engineers, which bore the fruit effectively in the form of the most reliable reactor ever worldwide. Passive security systems, independent of the operator, of a human error, of any other failure. Gravity-based is a major characteristic, major security factor here. No feed, no power supply from the outside for at least 72 hours in case of major failure, of a critical failure. As you can see on this slide, the steaming, cooling, and the steaming and cooling 72 hours is time enough for getting the reactor cooled. Standardization and simplification. This is quite indicative. This slide, you can see it in terms of nuclear island footprint, as compared to the other reactors presently present and operational in the market, including compared to SMRs. New scale, 12 modules. Take a look. The closest to our solution. See it in megawatt terms. So energy produced by AP1000 can be used for heating purposes, I already said, for production of water desalination, hydrogen production, energy storage, and whatnot. All this being CO2 emission less, clean energy. We cooperate with companies, with different entities, showing them this chart. This relates to safety systems, security system, quality systems. The island is going also in Poland to be built to this particular standard, obviously. We are holding talks with our potential partners, including contractors and their subcontractors and so on and so forth, to see whether they're capable of delivering their jobs according to this standard. There's a qualification system, classification system, which we have launched for cooperation with our suppliers. contractors. First, we make them familiar with the technology and its intricacies, then we identify the gaps, if any. We audit to qualify, to requalify the bidding procedure, then comes over the tendering itself, then the contracting, then the implementation phase, the construction and stuff. This is a nuclear quality assurance system related to or based on the ASME criteria or standard. We've already entered into talks with about 55 Polish potential partners, prospects, clients, if you like. Large size facilities is our specialty. Steam generator, valves, bolts, I don't know, pumps within the reactors. We have to be reliable, definitely, but the structure of AP1000 is modular, and there is a chance for Polish contractors, builders to develop such facilities up to our standards, given the Polish realities, and within Polish realities. To this end, we are going to cooperate with our Polish partners in order to make them work according to our standards, to introduce them to our standards. That may be better phrasing. On a partnership basis, obviously. Just to end with, we strongly believe, having been for 2 years now present in the Polish market. We are based in Krakow with a company with 200 of the staff, and we are now recruiting our personnel for a Warsaw office. This is going all in all to be a great challenge for Polish economy, science, research, business. So debates, discussions, public ones, should be held as frequently as possible to make people aware of what the nuclear is all about, why this type of power, why is it beneficial, useful for Polish economy. I'm staying with you anyway. I have finished with my presentation. Thank you very much for this very interesting presentation, and I hope that the listeners are happy with what they heard. As usual, we have not too much time. Just one question, if you will, anyone. If there is just one question from the floor, so please try and address it. Mr. Jacek Baurski again, not using the mic. I haven't presented one of the slides, you know. Bechtel is one of the most reliable contractors worldwide. Construction specialists, this is what I mean. We are based on a Polish and a Czech project. Possibly we will include some other projects from elsewhere, I mean. If we speak in terms of division of responsibility or work, the responsibility for the nuclear island is Westinghouse's. For the conventional island and BOP, Bechtel is in charge. As of today, we are debating certain structure for implementation, for efficient implementation of the Polish project in cooperation with foreign partners. The next one to go is Mr. Wojciech Won from Nuclear Hydro Power Corporation. You're kindly invited to take the floor. This corporation boasts its 4 reactors having been built recently. 3 of them are operational now in the United Arab Emirates. So we expect a successful story for Poland as well. Thank you very much. 30 minutes for you to go.
The floor is yours.
And thank you, Professor. Dzień dobry. Is it right? Hello, everyone. Thank you for being here. My name is Wojciech Won from KHNP, also South Korea. Yeah, I'm very pleased to be here and to attend 11th International School on Nuclear Power on behalf of KHNP. This is my second visit to Poland. Last year I went to Krakow. This year I'm Warsaw. It's really a beautiful city and modern city, I think. Yeah, I would like to thank organizers of these school programs for giving an opportunity to present. And actually, I have joined the KHNP in 2010. Since then, I have been in charge of plant improvement and refurbishment project of steam generators, turbine, and generator at Hanul nuclear power plant in Korea. Currently, I am working in Poland project team since this January. Today, I would like to talk about the topic of KHNP solution with APR 1400 in Poland. So let me start my presentation. So table of contents for this presentation is as follows. So let's look at KHNP overview. KHNP is one of the world leading players in the nuclear industry, and it is the largest power company in Korea, which generates approximately 28% of the domestic electricity demand. It is a government-owned company with high credit rate, and up to now we have constructed 34 units in home and abroad. Now we are operating 24 units, and its total capacity is almost 30 gigawatt. Also, there are another 4 units that is under construction with APR model. It includes 3 in Korea and 1 in UAE now. KHNP is also supplies electricity with hydropower and pumped storage electricity, hydroelectricity, and solar and wind power. So this is the location map of nuclear power plant in Korea. We are operating 5 nuclear sites, which is Hanul, Wolseong, Gori, Seoul, and Hanbit. We also have its own central research institute. So, and Gori and Seoul site are the largest nuclear complex in Korea. When it comes to construction, currently there are 3 units under construction. From next year, we will start another construction with 2 APR model, which is named Sinhanul 3 and 4. KHNP also operate research center also have. We have 2 power plants that are permanently shut down. Gori 1 and Wolseong 1, they have fulfilled their mission to produce electricity. And they are being prepared for decommissioning. So let's look at history in KHNP. KHNP's history of nuclear business covers more than half a century. In the 1950s and 1960s, Korea's nuclear power industry was the initial stage with basic academic study and initial research stage. The oil shock of the 1970s was one of the triggers that made us realize the importance of its own power ability, which is nuclear power and another power solution and energy security. So we started construction Kori 1 in 1971. And in the 1980s, the participation of domestic suppliers and companies in the nuclear sector gradually expanded. After years of experience, we were able to achieve technology self-reliance, developing our model such as APR 1400. In 2009, Korea was selected as the supplier of United Arab Emirates nuclear power project. And Korea became one of the few nuclear power export country, which was very sensational at that time. Through UA project, we could let the whole world know about a small but strong country in the Far East developed it enough to export nuclear supply. From 2010, we have continued research and developed to improve and advance APR model technology. And I believe the strength of Korean nuclear power industry is the accumulation of the know-how in construction and operation that has continued uninterruptedly. Repeated construction over the last 50 years has accumulated construction ability and technology, and the participation of domestic companies has supported significantly to the expansion of domestic market and growth of jobs. In addition, the government support program for R&D has been the foundation for technological advancement. So I would like to share a bit more about the status of APR 1400 operation and construction. In Korea, we are operating 3 units, successfully operating Seoul Unit 1 and 2, Shinhanul Unit 1. Another 3 unit is under construction, Shinhanul Unit 2, Seoul Unit 3 and 4. Next year, we will going to start the Shinhanul Unit 3 and 4 construction. And in APR 1400 in UAE, 3 units successfully is now operating. 1 unit is will finish their construction next year. So APR have received design certification in Europe and United States, as well as standard design approval in Korea. In 2017, APR 1400 got EUR certification, which is European Utility Requirement. And in 2019, it received design certification from US NRC, and it is the first reactor outside the United States to achieve both design certification from US and Europe. APR 1400, that is advanced power reactor, that is a third generation light water reactor with capacity of 1400 megawatt electron with 60 years lifetime. It has enhanced the safety features compared to the third generation nuclear reactors developed by another country, and it has a high ability to cope with fires, flood, earthquake, and external shock, also post-Fukushima solution. As an improved safety system, it features a 4 independent drain safety injection system. We also have a mitigation of severe accident and beyond the design basis external event. And we we have a fully digitalized INC system in the MCR. So most important thing is KHNP is ready to be flexible to modify APR 1400 design based on the site characteristics and requirements from the owner and regulators. So the third topic is strengths in KHNP. So we have the fully completed ecosystem, which is supply chain. As a result of continuous and successful construction and operation on nuclear power plant over the past 50 years, we established a well-organized and efficient supply chain that is optimized ecosystem of nuclear industry. We also believe the participation of local company from Poland to expand. So, localization is probably one of the biggest considerations for Poland nuclear program. In Korea, KHNP often says, when our suppliers develop, we can develop. Supply chain and localization should go hands in hand. That is the reason why KHNP needs to cooperate with local companies. So let's look at the UA project. We won the project back in 2009. We supplied for API unit and fuel and operation service. And Baraka Unit 1, 2, 3 have already started their commercial operation, and Unit 4 is still construction, which is commissioning stage. When all the units are put into its operation, they will be responsible for about 25% of UA electricity demand. So there was so many challenges. As you may know, the UA project took place in the desert. There were so many challenges that need to be addressed in order to proceed with construction. Working hours has been adjusted due to the weather condition, and another challenges was adopted the cooling system to hot weather condition. BMPP project was the first overseas nuclear project led by Korea. In addition to extreme environmental conditions, such as heat and dust, there were many obstacles, such as cultural difference, lack of infrastructure due to being the first nuclear plant in the UAE. However, we were able to overcome challenges with decades of experience in domestic business and the management system that systematically manages a multinational workforce from 50 countries. With all these efforts together, we were able to achieve one time, one budget delivery. It is showing the pictures flowing Baraka plant is being completed from the desert sand and the whole power plant. So, KHNP operates a nuclear graduate school whose name is King's for students from all over the world. So far, 447 students from 29 countries have successfully completed their studies. In 2023, 5 students from Poland was admitted, and they are pursuing their studies in the nuclear field. We also invite students from Poland and Czech Republic for summer program. They get a chance to visit Korea nuclear power plant and major nuclear suppliers, which is in Korea, every summer to broaden their horizon. So let's get into construction of APR 1400. The process of building a nuclear power plant can be roughly divided into 5 sections. Of course, each phase has thousands of sub-activities. The project preparation phase consists of feasibility study, EIA, environmental impact assessment, and site survey, and signing major contracts and obtaining adequate license permit. And civil works begin with the site grading on the selected site, and it also includes excavation for the center of the reactor building. After civil work, first concrete is poured and construction work really start. In terms of reactor containment building work, RV set is one of the most important milestones. As the building work progresses, the installation of major equipment is also carried out. Once the installation of equipment is complete, testing stage is carried out. Major steps include CHT, which is cold hydrostatic test, and HFT, half functional test. So each task is highly interrelated. So it is also sophisticated business sophisticated business management ability, and process management also required. And it is showing the key pictures of civil work from site grading to excavation. It also shows the main steps of reactor containment building structure. Once the building work is done, the installation work for main facility is as followed. The main component is, I can say, a reactor vessel, steam generator, turbine and generator, and which is also the key system INC in MCR. What is the most important thing during the construction process? So this is a kind of question. There would be so many possible answers, but KHNP's answer is safety. Creating safety working condition and environment for workers is KHNP's basic attitude toward the construction and operation of MPP plant construction. Technology helps us, but it is all done by people. So safety is first priority for KHNP. You already know the KHNP is working with PG Park Energy Indrome. In this section, I will briefly give an overview of Pantana project. Pantana project is a key initiative of KHNP with the full support of Korean government. I am personally very honored to participate in the Poland project. The project is to build 2 APR reactors in Pongtnuk, Konin, to provide reliable and clean energy to the Polish people and business. Once operation starts in Poland, they will provide approximately 12% of today's electricity consumption. What we have done and what we'll do. It's been 6 months, about 6 months since we signed the LOI between corporate and MOU between governments. During this time, there have been numerous talks and cooperation between both companies. I would like to say that this solid cooperation is based on the trust PG Park and KHNP shares a common goal of establishing energy security and providing clean energy through the construction of MPP. Going forward, we are working together to conduct a feasibility study and detailed site survey and environmental impact assessment between 2023 to 2025. EPC contract is targeted to be signed by 25. And finally, we expect to start supplying electricity to Polish grid from Pątnów Nuclear Power Plant Unit 1 in 2035. So, before I conclude my presentation, I would like to mention once again the following advantages of KHNP. The nuclear industry will be with Poland for at least 7 years. There will be many more challenges, changes, and developments in the field of industry, home, education, securities. KHNP will be a faithful cooperation company and over Polish nuclear business. And ladies and gentlemen, let's move forward together. So thank you for listening. This is all I have prepared for today's presentation. Dziękuję.
Thank you very much for your interesting and most instructive presentation. Before I ask for questions from the floor, I should like to ask one question of myself, of my own. Namely, you have shown that the time of construction of Unit 1 was just as it should be, 6 years, which is a wonderful achievement. Yeah. But actually, the unit has been connected to the grid much later, I believe about 2 years later. And I have heard that this is due to the difficulties in preparing Arab crew for competent and safe operation. Could you say if it is so, and if it is, how did you solve this problem?
Yes, we will have more challenges, Professor said. But our plan in Korea, we plan to construction of nuclear power plant before 15 years and 20 years basically. But at the time it was not feasible. But 10 years, believe it, really, I think 10 years. Sometimes it's likely to be long, but very fast, because of you also know we are aging. 10 years ago, you can believe your preference, but now we will have more challenges, and I can say that KHNP has ability to solve those problems with Poland. Yes, thank you.
Dziękuję bardzo. Czy są pytania?
Thank you very much. Are there any questions from the room, from the audience? Go ahead, please. Zbigniew Gryglas.
Concerning your policy on local content, as you probably know, our main aim is not only just to transform Polish energy sector. We want to also involve as many as possible Polish companies in the building process, but also in the maintenance and just production of energy. So, do you plan to involve also Polish companies in the process, and how it will works?
Yes, the localization and the making the Polish local companies into our supply chain and to help us to maintenance our nuclear power plant. And all this work is in the middle of our plans, and we are trying to find out the best solution. And actually, it is an initial stage, but we are broadening our cooperation with Poland industrial sector, with, for example, IGOS educational program. Yeah.
Thank you very much. Unfortunately, our time is up, but we have a lunch break, so you will have an opportunity to talk to our presenter. Thank you very much indeed.
The next presentation comes from France, EDF of France. René Lévy of Framatome is going to cover major characteristics of EPRs and their perspectives. René is a technical expert for hydraulic section in Framatome, and he's been a nuclear expert since 1978, at least. Heat and flow research, advanced pressurized three-dimensional methodology, transient conditions, and normal operational conditions in NPPs has been his specialty as a researcher. Thank you very much indeed.
This one. Okay. I am working in Framatome, in the safety department, thermal hydraulic department, emergency operating procedure, transient analysis. And I made this presentation with some slides that I merged with Thierry Deschaux, who is a representative for EDF in Poland. So my presentation will be split into three parts. The first part will be dedicated to what was the story of nuclear plants in France. So I think it's important to have this in mind because 50 years ago we have exactly the same story. I think that at the beginning of nuclear plants as in Poland. After that we will see what are the main differences that we have introduced within the EPR, and we will see what are we for the commissioning for EPR and what are the future perspectives. Okay, thank you. So for the nuclear technology, what is important is that in the 1970s, just after the oil crisis, the French government decided to launch a program for French fleets. And at that time, we used the Westinghouse technology, but in order to have benefits regarding the cost, optimization of the cost, it was very important to have this series effects. So what were at that time the key ideas for the success of the story? It was the first one is that we have a centralized management in order to reduce the construction cost, but also to reduce the planning, the time schedule. We had also some cooperation between the industrials and the government and the research also. And the government has also at the time decided to make a closed fuel management, so to optimize the waste for the nuclear plants. And he introduced this this consideration in all of the overview of this policy. So if we are looking at what were the modifications, we started with the Westinghouse license for the 3 loops. After that, we made some modification. So if we look at the duration between the construction start and the first grid, at that time, the duration was between 4 and 6 years. It was in the 70s and in the 80s. After that, we made some modification for the 1300 megawatts. The duration was slightly increased between 7 and 8 years. And after that, for the last generation, the last plant, it was N4, and we can see that there is also an increase. It was in the 80s and 2000s. What were the reasons for that? Each time we introduce some modifications, we have also to face some things that we do not entirely know, because when we construct some nuclear plants, it's not only paper, but it's important to have these realistic conditions. So for N4, for instance, we have to face some problems for the overflow that we have for the reactor plants, but also some fatigue analysis, for instance, for the residual heat removal system. If we look at what are the fuel that we used here in the French fleet, we use 3 different fuels. The first one is the uranium that which is enriched until 4%. We also use MOX, which is a mixture between plutonium and depleted uranium. The aim is that with 7 fuel assemblies which are burned, yeah, we are capable to build a new fuel assembly. But in order to do that, as we have a lot of isotope which can capture the neutrons, we have to increase the isotopic vector and to increase also the enrichment. And the other fuel that we use is the repressed, the recycling uranium. So we have 3 types of fuel that we are using in the French fleet. If we look at the modification, at the beginning it was the 3-loop plants, so the same design as Westinghouse. We decided to make some modifications, so we are within this technology CPU0, CPU1 and CPU2, some differences regarding the main control room, but also some modification controlling the additional cooling circuit, for instance. And we have also introduced a new control for the rods, so it's the mod G, because at that time, as there were a lot of plants on the grids, we wanted to operate in load follow operation. And if you want to operate in low follow operation, it's not obvious if you use A mode. So G mode is more adapted because you have to insert the rods depending on the power, and if you want to control, for instance, the axial offset, axial power shape, or if you want to control the temperature, it's more easy to do that only with one RB bank. So here in this slide, we can see that for the protection system, for instance, it was derived from Westinghouse for the delta T protection channels in order to avoid risk of fuel melting or risk of entering in a DNBR boiling crisis. So the principle is that we can operate the plant in a trapezium in the normal conditions, and we have protections in case of accidents, and depending on the axial power shape, we can make this protection closer in order to avoid to have some peaking factors which have an impact on the safety analysis. Regarding the modification that we have introduced for the 1300 megawatts, we used at that time new technology regarding the instrumentation. Before we have two positions for the X core, and with 1300 megawatts, it was possible to make the reconstructions of the axial power shape based on six axial measurements. And at that time, the sensors were also classified, so it was possible to have robustness and safety information regarding the axial power shape. And we use also digital technology. And with these sensors, we were also able to have online the reconstructions of the power and to monitor it, and also to have the modification online regarding the power and regarding the risk of DNVR. In this slide, you can see a picture for the main control room. It was more modern, more ergonomic for the operator. If we look at the duration for the startup of N4, I already said that we had a break in the residual heat removal system because of mixing zones. And at that time, there was some different, because we have very big differences between the injection on cold leg and hot leg. And we made some modifications regarding the position of the weddings, regarding the T-zone and the mixing areas. Okay, today, what does the nuclear power represent in France? So we have 56 operator reactors. We have a reactor which is under construction, which is EPR. And you can see here the modification regarding the number of fuel assemblies, also the number of nuclear plants that we have. So the majority is 3 loops, but we have also 4 and 4, for instance. The modification regarding the steam generator, for instance, if we look at the steam generator pressure, we have an increase of the saturated steam generator pressure during this evolution. And it's also the case for the EPR, because EPR today, for instance, it is 78 bars for the saturated pressure. What we have, you have also to have in mind is that on the French fleet, we have also every 10 years periodic safety reviews. It's the case in all the countries. We have to take into account all the feedback experience that we have. We have also to deal with equipment aging, for instance, obsolescence, improve the safety of the plant, taking into account new standards. And it was done for EDF, for the French fleet, in order to take into account this. There was a complete overhaul of the primary and secondary circuits during this periodic safety review. I take an example here of what were, for instance, the evolution of the operating time for the operator. At the beginning of the design, we asked the operator to act within 10 minutes after a reactor trip or after a signal which is important for the safety. And during the different 10 years outage, this time has increased. Today we have to consider 30 minutes because it's impossible to make the right diagnostic within 10 minutes. And with the new generation, with the EPR, we have also a lot of automation regarding the safety protection in order to increase this time for the operator. Okay, here I took an example of what is done on the French fleets today regarding the renovation of the equipment, for instance, the modernization of the control room, and also some modification that we have done after Fukushima. For instance, we have introduced a new ultimate diesel generator in order to provide some electricity in case of flooding, for instance, and we have put this new system located in some elevation in order to avoid the risk of flooding. So in France, with EDF, there is a big capacity to use the nuclear plants in order to adapt to the grids. It's very important to have this also in mind, because when you produce some electricity, you have to accommodate the electricity depending on the demand and depending on the price that there is on the market. We have a lot of load flow operation. We have also frequency control in order to control the frequency of the grids around 50 Hertz. Sometimes there are unexpected grids, and we have to withdraw the roads very rapidly to accommodate this variation, this disturbance. And also sometimes we have also to operate in extended low power operation in order to make some optimization regarding the schedule outage, for instance. So what are the main modifications that we made within EPR? EPR is the synthesis between two technologies. The first one is the technology that we had in France with N4, but also the convoy technology from our colleague from Germany. And the project was initiated in the 80s using this technology. So if we look at, for instance, what are the components used in the EPR, some provides from the convoy and other for the N4. You have here an overview of the layout of the plants. There is the reactor building, but also fuel building and several divisions, 4 divisions for the Sauvegarde building, access building, turbine island, and office building also. So for the nuclear island, it's the principle of PWR. With fission, you produce some energy. You use this energy in order to make some conversion to a thermal energy and to provide steam to the steam generator. Based on that, with the steam of the steam generator, you can make some electricity with an alternator and conversion it. What are the main modifications that we have implemented in EPR? We have improved the redundancy, and we have also used the separation concept. So we use 4 trains for Sauvegarde systems. We have also 4 electrical divisions, 4 diesel generators, and 2 station blackout generators. We have also modified the INC. We have, for instance, made separation between the sensors and the signals which are used for the monitoring and those who are used for the protection in order to avoid pollution, INC pollutions, but also to make some priority between the signals depending on the safety classification. We have also improved the human-machine interface. It's more ergonomic, and also improve conditions for the operator. And with these concepts, we assess that we have a reduction of core damage frequency of a factor 10. What are the components for the reactor pressure vessel, the steam generator, and the pressurizer? The principle is that we used larger volumes. This can provide additional time for the operator before severe accident, for instance. The reactor coolant pumps, we have used the same technology as N4. We have shaft seals, and the feature that is used is that in case of a station blackout, for instance, or failure of the seals, there will be no break which will occur. We use also a heavier reflector. So the aim is that with this heavier reflector, we can make some retro diffusion of the fast neutrons, and we can save some neutrons for the fission. We can see here an overview. It's a core baffle which has been replaced by stainless steel, and there is also no risk for bolting, for instance. risk and melting. And we make the estimation that we can, with this concept, we can improve the fuel cycle cost from 1 to 2%. For EPR, we have also introduced the core melting, a system in order to collect the core melting, to spread it in an area and to cool it in. So it's a new concept which has been developed with a core catcher which is capable to cool and to contain the molten corium. Okay, and to do that, we have some here heat exchangers, but also we are able also to control the pressure on the containment with a spray nozzle, for instance. We use also different systems in order to be sure that they are redundant, that they are physically and geographically separated. Both for the mechanical equipment, but also for the electrical equipment. For instance, if we consider one division, only one division is able to fulfill all the functions for the safety, because in one division we have all the functions that are allowed to reach the safety conditions for the reactor. What we can also see is that for two of these divisions of this building, we have they are bunkerized. The aim is to strengthen the resistance to external events such as airplane crash, for instance, or fire or flooding. In this picture, we can see the location of the different COGENERATION building. We have also introduced for EPR a new instrumentation. We have, for instance, X-core instrumentation if we want to monitor the neutron flux, but we have also in-core instrumentation and two types of in-core instrumentation. Movable instrumentation in order to make the calibration of the core, and also a fixed instrumentation in order to build the DNBR online or to build the linear power online. And all the instrumentation is introduced from the top of the reactor pressure vessel head. If we look at the movable instrumentation, so the principle is that we use vanadium balls, which are inserted from the top of the RPV. Then they are transported into the core. After 3 minutes of radiation, we send them in a bench, and we see the activation. And based on that, we are able to make a reconstruction of what is the radial power distribution and also axial power distribution. For the fixed instrumentation, we use neutron detectors, which are inserted. So what we call SPND, we have 72 SPND, and based on that, we are able also to make the calculation online and the surveillance and monitoring and protection of the core. For the core performance, we consider that we are able with EPR to fulfill all fuel management. It could be in-out, out-in fuel management with different length cycle length for the depletion. And we also consider that we are capable to save some uranium consumption with this design. It is also consistent with the MOX. We can put MOX in EPR. Regarding the maneuverability, we have increased the maneuverability regarding the needs on the French fleet. So we have also, for instance, partial trip if an event happens in the core. it's possible not to drop all the rods, but only partially the rods in order to maintain the reactor in a safe state. And after that, it is possible to restart the plant without having a shutdown, for instance. So we consider that the availability factor has been increased, that it is possible to make short scheduled outages, that it is also possible to have in-service inspections and maintenance during the operation of the operator of the plant, operation of the plant, and we have also limited the risk of reactor trip with partial trip. Regarding the preventive maintenance during power operation, it is possible to have some maintenance during operating operation and to have one safety train, for instance, which is not available because we have considered it during the safety demonstration. Here we can see what are the zones, the area which are accessible to the operator during the operating plant, and which are the ones which are not accessible. You have here a picture of the human-machine interface, which is more ergonomic with different panels for the operator. The aim is to minimize the human errors because it's the risk that we have for all the plants, the risk of human errors. Regarding the computerized INC, we have here different levels. So level 0 is the level for the sensors, the switch gears. Level 1 is the system automation, so we have here, for instance, the protection system, also the control, the alarms, the safety automation systems, and in level 2 we have the supervisions for the operator and to monitor the plant. For each level there is a classification, safety classification, which can be different. It's very important also to have in mind that when you plant, when you build a nuclear plant, there is a very big effort for the INC architecture. It's very important. Here it's an example of the human-machine interface design, for instance, with the different panels that we have. Okay. Now I will present where we are on the commissioning aspects for EPR. So we have started in China 2 EPR. You can see here a timeline for what was the first construction, the first concrete, and when it was in commercial operation. So we have 9 years between the start of the concrete and the commercial operation for Taishan 1, but it was also the case for Taishan 2. You can see also the different phases that you have. When you start a new build, there is the construction, but after that you have a lot of tests to be performed. The cold functional test, during this test, for instance, there is an hydro test in order to show that there is no leak, and you increase the pressure of 270 bars. It was the case for Taishan. After that, you had hot functional test when you see if all the systems can answer to their requirements. After that, you have to fill the core with the fuel loading, then the first criticality, and after that, a lot of operation during the power increase. The power increase, for instance, the duration could be 10 months because you have several steps between the beginning and the full power and also the performance of the plant. You know also that for OL3 we have also reached the commercial operation in April. It was very recently. And today, OL3 is the most powerful NPP in Europe, and the third EPR which has started in the world. If we look at the other EPR which is under operation, not exactly, but will be in the next year, it will be Flamanville in France. So our expectation is to make the fuel loading at the beginning of 2024, and then to make the first criticality after that, grid connection and commercial operation. On HPC in Clear Point, we have also two EPR which are under construction. So we start the construction in 2019, and the commercial operation is expected to be in 2027. And you can see here different steps in the construction. Installation of the first section of the liner, it was in 2020. Overview of the site in 2022. And at the beginning of the year, for instance, we have delivered the vessel. We have here a picture of that. What we intend to do in the UK is that we want to make a replication. So we have discussions to build two EPR, just like HPC on the site of Sizewell C, and it will be a replication of HPC, exactly the same design, no modification compared to the design of HPC. And we have launched the first manufacturing of some components for Sizewell C. What we intend to do in France, we want to also have some modernization in the production of all the components. So there is a program which is called EPR2. So we want to take into account all the feedback experience that we have of EPR, because we have some difficulties with EPR. We want to take it into account in order to optimize the constructions, to reduce also the time schedule, and to a degree also the cost. So in France, we intend to build 6 new, it will be EPR2 nuclear reactors. We said by 2050, but the first should be commissioned in 2035. And in that way, we want to improve capacity to build, but also to make a modernization of all the manufacturing that we have, and to use also 3D models and digital, for instance, for the engineering. What we intend to do is, for instance, to build 16 steam generators, to manufacture 16 steam generators within 3 years. But also, we are working on what we call EPR 1200 megawatts. So it's a reactor which has exactly the same characteristics of EPR or EPR2, but we want to reduce also the power of this reactor, because in some countries, for instance, some countries consider that EPR is a too big reactor because they have not the capacity on the grids in order to have this electricity production. So we want to build EPR adapted to 3 loops, for instance. And you can see here what are the modifications that we intend to do compared to the EPR. If we take an example, the vessel will be smaller because we will have less fuel assemblies, 177 instead of 241, for instance. We will have the same steam generator. We will also adapt the size of the heavy reflector. We will have the same primary pumps, the same CRDM. And for the cooling lines, for instance, we will have exactly the same diameter, the same lingots, but we will cut the length depending on if it will be used for EPR2 or if it will be used for EPR 1200 megawatt electric. and we have also a smaller pressurizer. We have also some discussions with different countries. So, for instance, with in India, we have advanced discussions for free EPR on the site of Jagdalpur. We have made some studies for local analysis, for instance, for the bright preclusion concept. We have also some discussions with the Czech Republic for Dukovany 5. And so we have 3 EPR in operation, 2 and nearly 4, 2 under constructions, 3 in France, which will be ordered by the government, and 2 for size well C. But we are also working for other products. For instance, in France, we are working on SMR. It's a new world technology, so it is a technology that we have taken from Technicatom, which is a submarine company. We are working on the feasibility aspects because it's very complicated to merge with this technology, because in the paper all seems to be very ideal, but when you want to make the constructions and to see if it is you can manufacture the equipment, it is more complicated. So New World is the capacity is 340 megawatt electric, and here you can see the characteristics. I think I made here a mistake. You can use it for 24 months. The duration, it could be 60 years. And the fuel assemblies in core, for instance, it is you have 76 fuel assemblies. So the principle is that you have here two reactors which are underwater. And with this concept, it is possible to limit the risk of several accidents. So in this slide, you can see the different components that we are looking for New World. We have some work on the lower internals, but also for the upper internals. For the pressurizer, it will be quite different for the pressurizer that we have in EPR. For the containment, it's just like an egg, but also we will use a new steam generator with plates, with micro, which is very different from the steam generator that are used with tubes. And you have also a timeline for what is expected to be in France, detailed preliminary project, so it has been started. We will have a detailed design and licensing between 2025 and 2030. And then we expect to have a first concrete, but it's not sure, in 2030, and commercial operation in 2035. So it's the end of my presentation now. Do you have some questions?
Bardzo dziękuję, René. To był bardzo obszerny, ciekawy referat i pokazywał rzeczywiście ogrom prac robionych we Francji.
A large presentation showing the enormity of the work done in France. Any one of you willing to ask a question to dear Mr. Speaker from France? You're welcome.
Aha, przy okazji mówimy po polsku, przepraszam.
Speak Polish, please.
Mówiłem po angielsku przez pomyłkę, ale prośba jest do wszystkich mówiących po polsku, żeby mówili w naszym języku.
Apart from those of you who speak Korean or French, and use the mic, please. Use the mic, otherwise you can't be heard by the interpreters in the booth, which is the case right now.
Mam pytanie co do kanału doprowadzającego korium do przepalone rdzenie. Chciałbym zadać pytanie, czy sam kanał jest...
To the, is this duct cooled? Is this duct plated or lined with a cooling material, the one that provides this substance, as well as the tank? Or are there any technological solutions provided to prevent the corium concentration in the duct before it gets heated up in the vessel?
You are speaking of EPR or for...
Odnosi się pan do EPR-u.
EPR? Okay. So for EPR, here we can see here the photo. I think it's here. Core melting here. Okay. If there is here a risk of core melting, for instance, it will be put in some areas here, and it will be sprayed. So you have the capacity to make retention of this core melting during a long time. Okay. So if you are speaking of the core retention, so if there is a risk of core melting, for instance, you will have the core which be sprayed in this area, just at the bottom of the vessel, and in a regions which we will use with passive device a lot of water in order to be sure that it is possible to have a cooling of this aquarium, for instance, and also in avoid to have overpressure. We will have spray nozzles. So there is a cooling system which is based on passive device in order to be sure that we can keep the aquarium a long time without any risk of exposure, for instance, and any risk that it will contaminate the underground, for instance.
Dziękuję bardzo. Było jeszcze jedno pytanie zgłoszone z drugiej części sali. Nie widzę w tej chwili, kto z Państwa podnosi. Bardzo proszę.
Ja mam takie pytanie, bo na prezentacji widziałem, że wśród tego wypalonego paliwa MOX znajdował się oprócz uranu i plutonu ameryk.
Americium was also shown. Americium was shown, and using the third generation reactors like EPR third, yes? Can you burn up completely those trans-plutonians, including americium, or rather the fast reactors, so-called, would be used for the purpose? How does it work? What kind of solutions have you provided for?
Okay.
Can you burn Americ here in third generation reactors? Fast reactors?
Today, the French government has decided to stop the fast reactor, so it's not possible to use americium, for instance. But in the mixed oxides, so which is a mixture between plutonium and uranium, we have 5 isotopes of plutonium, but also americiums. And when we can put a part of this isotope in order to be burnt in the fuel management. So for EPR, but it's also the case for the free loops. Today in France, we have a fuel management which is called MOX parity, for instance, and each time we have a new loading for the fuel assemblies, we use 12 fuel assemblies which are with MOX, and we use 23 assemblies which are with uranium. There is a mixed, for instance, for the free loop plant, and we can also use MOX for EPR.
Dziękuję bardzo, René. Dziękuję Państwu za wysłuchanie referatów i aktywny udział. I teraz zapraszam
wszystkich na lunch. Thank you very much for your active and proactive participation. Have your lunch, take your time, and in 60 minutes' time, let's reconvene in this place.
Good afternoon. We shall postpone it by 10 minutes, starting at 3, so everything will be moved forward by 10 minutes. Thank you. Good afternoon. Welcome back after lunch. We shall start with next session. All right. Close to the first presenter, Professor Wacek, author of the almost 100 papers, transmutation, neutron dispersion, non-proliferation of nuclear arms, nuclear reactors, grid energy, Professor neutral physics. 6 years we worked at KTH. Who has encouraged you to work? The Professor Wacław Gudowski. Good afternoon, ladies and gentlemen. After such a nice introduction, I just wondered now how to make this presentation, not to advertise any particular solution, but my privilege, in fact, is that out of many reactors of the fourth generation, worked with the majority of them. My first topic at AGH was the application of HTGRs for gasification and liquidation of coal in mid-1970s. My PhD thesis sodium-cooled research reactor. Then I was in a scientific council for the cool reactor at Cinque University, and for 15 years I've promoted the application of liquid metallic reactors, and I can be proud that together with my American colleague, we are two people who have drawn this technology out of the Russian military database. 1997, I refer you to the picture. I've smuggled $60,000 to Russia to pay for patent. There were no bank transfer. Russians 2 days later said, for 20 years we will not earn on that. We do a workshop and we'll open it up for you. So I put back this $60,000 and smuggled again. So that was the beginning of the history of the liquid metal direct crystals reactors. Sorry, the agenda, fourth generation. Everyone says SMRs, 3, 4, 5 generation reactors. I'll make a review of SMRs. I'll tell you about more important. I'll focus on HTGR for some reason. It won't be HTGR of a unit type, only because this other one is less known in Poland. And Agnieszka will tell you about the unit, modular one, and Tomek tomorrow afternoon. Then I'll walk you through the reactors on melted salts and liquid crystals. What's the fourth generation reactors forum? I had the privilege and pleasure to be in the group which in 1999 obtained instruction from President Clinton two groups of future reactors. Transmutation were to develop an international program that would somehow focus the end of 1990s, dark age for nuclear energy. No one wanted to even listen to it. So we had this international program to focus on pre-commercial development of reactors for the future, not the revolution. One of the prerequisites was replicability. That was important. And why not light water reactors? Oh, you know, it's already the business. These reactors will develop by themselves. So the group working team was created, and we just wondered how to communicate with the project. And someone got this idea of generation. It's like in people, it's generation 1, 2, 3, 4. And hence the concept to describe for society the development of reactors. One very important sentence in the instruction by President Clinton was in the last paragraph. Don't let them try to build something. So, yes, why not don't have these reactors on the shelf? Yes, that's because the idea behind it was the pre-commercial R&D solution type. So there's Generation for International Forum, sometimes called GIF4 or GIF4. It was set up in June 2001. Here we have the countries participating, and you'll find out Argentina and Brazil is there. Once they learned that the forum would not deal with water reactors and they wanted to develop Kalina, so they said we would be only passive participants or members. And here you have, it was Ernest Moniz, Undersecretary of State, and under Obama, I think he was head of DOE. And on the left-hand side, you have this team, the group working, and Nobel Prize, Carl Rubio, but the next Nobel Prize winner. And in Washington, 1999, we created the basis foundations for it. And that's how we started to communicate that Generation 1 are reactors built at the beginning of the 1950s. Shipping port, Dresden, Fermi 1, Fermi 2, and Magnox, all sorts of them, as you can see. But from then, the predominant began to be the light water reactors. The second generation 2 is the one that from the 60s, they built over 15 annually, constructed at that time. BWR's President Kowalik was out of 450, 300 only 100 PWRs had developed slightly earlier, and researchers had a problem with this boiling water in the core. They wanted to fine-tune it, and once there was a serious production, PWRs dominated the market. And not mentioned by President Kowalik, on the 8th of December 1953, then President Eisenhower announced the well-known item for peace. So all the countries that did want to arm themselves obtained technology for free. So BWRs in Sweden or in Spain or Germany are in fact the same as BWRs designed by Hitachi. Some of the PWR reactors are also the fruit of that program, Item for Peace. This year it will be the 70th anniversary, so maybe reactors for not, instead of atom reactors, for Generation 3 was the one that in fact was designed after the Three Mile Island breakdown. They began to think about the core catchers. So it was system 80+. Generation 3 plus are light water ones that evolved from those. The ones we discussed today, like AP 1000, 1400, or WX. And fourth generation, the task was that firstly it had to be recyclable. So no dose of thermic neutrons, and cogeneration, the use of heat, synthetic fuels, air conditioning, cooling, and desalination of seawater. In Poland, it's not that important, but globally it is. And the objective of the innovation was in balanced system or in sustainable system, good economics. Some wish list, good economics. You have to go through certain safety and reliability. Many of them have better solutions, resistance to the risk of proliferation and acts of terrorism or the. So that's how they defined system, good economics, under which there was that we had to replicate them. And 6 reactors under that generation, and working groups, one cooled with sodium. The problem is that these reactors were built earlier, but they were tested, and the greatest catastrophe was Superphoenix, economic breakdown. It didn't work as well as designed, but it had no problem with safety and security, but it didn't meet the conditions for the commercial reactor. So sodium was already tested, but as the potential in sodium as a coolant is regarded by many as good, I don't think so personally. What's most important is that you have a closed fuel circuit, so you can use and recycle. The second one was lead-fast reactor, including also bismuth and lead. The positive is that while lead melts at 319 degrees Celsius, is 140. So nearly 4,000 degrees Celsius difference. Temperatures that you can get out of it, in fact, it's about 430, the plant up to 800, but I think it's a matter of future. We didn't have those reactors commercially available globally, but that on bismuth and lead-fast reactors were developed as to propel Russian submarines, and they mastered that technology very well. And we got it from the archives from them. The third reactor, and you see all of those were big. They talk about gigawatts, you know, that was the perspective. They would reflect the size of light water reactors. As you can see, some were a human being, just for the sake of comparison, you have a figure. So all those were at the level of a gigawatt. The third reactor, gas-fast reactor, impossible to construct. The whole nature is against it. You will never meet, I'm quite aware of it, never the security requirements. You cannot use apply any passive mechanism. You have to have small mass of fuel, no heat catches. You have to keep cooling it with gas. No no matter what you do, you cannot build it. So basically, at the birth, it was bound to fail. Fourth type reactor was called a very high temperature reactor. Well, in fact, typical HTGRs with the lower boundaries is 700 degrees Celsius. The dream is to reach 1,000. Metallurgic industry would need it. They were built before the initiative of fourth generation. We had an American 400 reactor, pitch bottom. In Europe, we had in Jülich a cool reactor, but they say that this reactor has a huge potential and simply is included among, by definition, that we go towards higher temperatures in fourth generation. It says the difference, unlike in this, it's one through cycle, but in fact, in HTGR reactors, you can add thorium and replicate. There's a huge potential, and it would be a reactor that would replicate without the need to process the fuel. Difficult but feasible. Number 5. What a silly name. We physicians have a tendency to blow the social communication, neglect it. Critical, well, super critical. When people think critical person, well, it's critical state. Well, either be a saint or heal themselves. Critical, not critical means the same power, stable reactor, unlike something critical. So the name is silly, but they call it high performance water reactor or steam reactor, high performance water reactor. In Europe, we call it high performance light water reactor. Let me put it like this: not feasible, as well, even though supercritical steam has very good parameters in conventional setups. If I remember, over 350 power plants or power heat plants with this steam, but the problem is that to put it in the core of the reactor is not a good idea, because there are different, there's a fluctuation of density with change of temperature, and neutrons are sensitive to the density of the surrounding mass. So that was Radkowski who wanted to make them, and generally speaking, I think it's a dead end. No one wants to do it. They check, they test it. You cannot do it on supercritical steam, because it becomes like an oscillator of instability. And the last type was the molten salt reactor, temperature 600 to 800. It was already built in Oak Ridge, molten salt reactor, experimental one. For many years had a record of continuous operation or chain reactions, like 730 days or something. It kept on working. From the perspective of economy, it couldn't match the light water ones. Back in the 70s or 80s, Clico made it impossible to develop any reactors other than lightweight ones. Can you find a cheaper material than water for a reactor? No way. So the molten salt, there are two versions, either molten fluorides or chlorides. And fluorides, it's on thermal, because fluorides, well, all right. These are the countries that have are enlisted in under different types of sodium, that VHTR, high temperature, SC, WR, supercritical gas, fast reactor, liquid, metal, molten salt. You can see most of the participating countries, the generation, focused on the first three types, then supercritical dropped out from the competition. The group the project was nicely organized. We had 6 groups responding to these types of reactor, and then a cross-cut group, research groups that focused on fuels, irrespective of the type of reactor, economics behind it, risk management, and it worked for like that for 15 years. And all of a sudden, SMRs surfaced, and the International Forum overslept it of the smaller scale of reactors and making something going the other way, not replicating or not mending the inborn, let's say, errors. SMR is small modular reactor, although many of us would like to see it as a smart modular reactor. Smart grid, you know, it's very trendy. These are small modular reactors. They say up to 300 megawatts electricity, but Rolls-Royce promotes 440, and they say it's SMR. So it depends on how you judge it. They said about 1/3 to 1/4 of large nuclear reactors. The key positive features that can be easily adjustable to the requirements of customers. They offer polygeneration. They lower investment and license threshold. And here Poland has great input in this revitalization of interest in nuclear energy. In 2019, Michał Sołowow all of a sudden said, why nuclear energy is to be the state monopoly? He signed a contract with GE Hitachi, arguing that smaller reactors, smaller investment threshold, smaller risk, and all of a sudden they, in Europe, they joined in and they had these non-state entities that deal with SMRs. So it reminds us of the 1950s. My older colleagues told me, I remember these pioneers, they used to have like dice with fuel, moderator, coolant, and power. They tossed on the table to say, well, now we go to the government to finance this gas, or metal, fuel, power 300. That's what happened to SMRs. All of a sudden, renewed approach to them, and now 80 different projects. That's what we did with IAA on this scale. It's the stage of development here. Just see, under construction or operating. It's only very small. As now we have power and different colors. You can see in the upper right-hand corner lamps on HTGRs, liquid metal, heavy metal, and sodium reactors, MSR, is molten salt, and micro reactor that can have different issues. Now President Kozaczyk mentioned a Vinci micro reactor, which is not that cooled by sodium. It's called micro. Tomasz is going to tell us tomorrow is a gas, helium cooled one. So they reflect, these microreactors, this. So now the question is why the predominant majority of reactors are those of a smaller power. Most of the companies and startups were set up from 2005 to 2018, when the only proactive customer for nuclear energy were Arctic areas to explore a little more of oil or gas, the military, and possible off-grid application. People have noticed, like us, that the fees for grid are often higher than those for electricity. And there are many industrial entities that want to get rid of it. I'm not going to walk through all these concepts, but thanks to that initiative from 2019, Poland, Mr. Rajski said, we've become like, you know, fishing terrain from prime point to advanced reactors. All of a sudden, every entity wanted to have a contract signed with the supplier of small SMRs. It became very trendy, so we had to separate it out and to explain to those you advise, for example, how to tackle all that. So we made a list of the most interesting technologies. These are light water reactors on top, worth notice, taking notice, and you can see that it's precisely division between fourth generation reactors, 3+ light water, and here we have high temperature reactors on melt salt and sodium and lead, but there are no supercritical steam ones or gas reactor, because when people started to handle it, they know it's not a good solution. And here we've listed about 20 more interesting types of these reactors. It was our internal analysis that we made. Fortunately, like near OECD, and only 2 months ago they make SMR Dutch mold, so that's an assessment of 20 odd technologies. I skipped Russian and Chinese reactors because they are not interesting for today's market. But I'll tell you a little bit about Chinese. Russian reactors, for obvious reasons, they won't make an option for the next 50 years, most probably. So let's take a look. OECD made a ranking. You may have reservations to criteria. They use this such a way, but a strange way. Licensing, localization, financing, supply chain involvement, and quality and availability of nuclear fuel. And these were the criteria applied by NIA OECD. The yellow ones are regarded by NIA as not mature to such analysis. And what's the result? On the light water reactors, the leaders are Berenitz and NuScale. They are, according to the estimate, of a similar level. I think differently, but that's my expert's opinion. But in high temperature, the leader is X Energy with X100, but the power capacity is 8 megawatt, and it's a BWRX reactor. Second is MMR, modular unit 1. We'll tell you about, it's a high temperature as well. Now, well, you have slower scoring. The maximum was 36 scores. They are still far from perfection. And Salt, Hermes, and Moltex were the most promising. And metal, the lowest, it's odd, of most, number 1, TerraPower. It's a company funded by Bill Gates' foundation. They, years ago, they wanted to make a reactor with a moving wave or errant wave. Nice, but when it was no more possible to cooperate with China, they shifted to a sodium reactor. To be clear, as a physicist and having worked for about 40 years, I think that reactor where inside the core it has a strongly reactive material which is either flammable or combustible is not a good solution. And people are obstinate. They say, well, sodium is a nice material as a coolant or transport. It's less corrosive than lead. but unfortunately it's very reactive. So I just wonder until the day that I've asked a basic question to friends, why did you, oh, we've invested so much that we cannot stop, they said. Well, that's one of the possible ways, but you will see that we have a concept on the Swedish Sweden. I started in Sweden a dozen years ago, Westinghouse, not even evaluated here, and we miss, as a new player in the European market, very aggressive, very active. I mean, aggressive meaning, in the meaning, English meaning, and very dynamic. It's nuclear. They have collected all this competence, all this expertise of lead reactors built in Europe for over 25 years, since 1997, so it's 26 years. They even patented some things, ideas weren't always there, and the capitalists, well, oh, it's zero, time's up. Let's go forward then. We've BWRX with others, this is our own list, how you can compare, and it was the best, but mainly because it fits in very well to the program to replace the to nuclear units. Poland was the realm of units from 150 to 350, and it generates very well within that range. Plus the fuel available, so the criterion was the selection, very popular in the media. It's preceded by very thorough analysis, and it's not a political thing. You may have observation to some subjective assessments, but they give you a review in what's worth investing from the perspective of the time needs. Heat potential of various technologies, power of the reactor, available temperatures, plus different types of reactors. So you can do the highest temperatures, up to 800 degrees. It's a domain of high temperature reactors, slightly lower. There's on salt, melted salt, and melted metals, but still we're still far from the demands or needs of the steel industry, which has to decarbonize themselves. Some words about HTGRs. There will be Agnieszka and Tomasz telling about them. I wanted to tell you about the pebble bed one. I was in the scientific council of this, and I would like to make you realize what's the road from the research reactor to the industrial reactor. So the Chinese have obtained this for free, the whole reactor from Jülich. Jülich was liquidated, so they transferred blueprints, and they built a reactor, and it took them 6 years. That was a start. It operated until 2003. They made a very important experiment using it, showing that it can phase down itself with the full loss of coolant and control over reactor. Very public experiment, and they did it, I think, in very few countries they would allow for such an experiment. It was a crown argument that this reactor is passively safe. It will close down itself even if all the helium evaporates, and temperature will not exceed that of the fuel damage. This is how it looks like. The parameters of it. HTR had only 440 degrees temperature of water on water generator. We need 350, 360 in industry, and the pressure from 13 to 14 megapascal. And what is interesting, the pressure data, let's say 10 megawatt thermal reactor, and how it looks like in reality. was in this scientific council, 22,000 balls in this reactor, about 50 replaced a day and recycled. Quite a complex mechanism, but it's a dream for a physicist. It's almost a liquid fuel that we deal with. This is how it looked like. All the data for those of you who are interested in it. And based on that reactor, 15 years, after 15 years, they were bold enough to build a HTR PM reactor with the thermal 250 hooked to one turbine. And interesting solutions here. The 13 megapascal pressure in the steam generator and the helium loop 7-8. So in case of a breakdown in heat, the consequences can be dire. Quite a lot of water can come into it. So, and the number of balls in this 420,000, the replacement of 200 a day, 70, 80,000 a year, and that's they are circular again, so it's nearly liquid fuel from the process perspective. And the next step in China, they are building 600 units. So based on that, X-Energy follows the Chinese precisely, as they want to probably know how it looks like. Very similar elements. They have more elegant graphics, but the plan is that by 2030 they want to commission such a reactor. What's the problem with the ball interactive? The ball one has a good level of 200 of heat and of what the industry needs. MMR reactor is only 15 thermal megawatt and 5. So dilemma whether go towards more complex one, because make a startup and implement 165 megawatt thermal, about 660, 70 electric, and let's build it here based on the research reactor to be discussed by Agnieszka. 2 lines of these reactors, salt reactors or chlorides or fluorides. Maltex Canadian company, Skyros, they use balls in salt. They don't melt fuel in, but they use the pebbles and they don't mix the. So the coolant is very clean and never contaminated. It's close to my heart. Molten metal or salt, 500 terapower prism, eVinci, or lead by Westinghouse and nuclear, very active now. So this is how this nuclear looks like. Many experiments are used. This is Swedish sealer. What a difference between the 4th generation and these reactors. The problem is access to enriched fuel higher than 5 or 6. That's another. Which SMR is the best? The one that meets the customer's requirements and has a sufficiently high level of prospect for development. Thank you very much for your attention. Thank you very much. A quick question or two? Well, I'll answer during the break. Thank you very much indeed. Thank you very much.
Now, Agnieszka Bycia of the National Center for Nuclear Research. She works for the same department as I do, namely the section of nuclear power and environmental analyzers. Yes, indeed. Thanks very much for having introduced me. So I'm Agnieszka, a worker with NCBJ of Poland. I'll share with you a bundle of piece of information regarding construction, design and construction of a high-temperature reactor that is installed and operational in Świerk, not far from Warsaw, at the Research and Development Center of our organization. One of the basic categorizations, if you prefer, of reactors at all is their purpose, namely research-oriented or power or energy-oriented. Also, there is a division into electricity and heat or thermal power generated or produced by the reactor. So there are thermal reactors and so-called fast reactors, depending on the types of neutrons that are liable to the fission reaction within the reactor. Also, there is a bi-coolant classification, basically water, gas, molten salt, and molten metal reactors. Almost all of them have been covered in a variety of aspects, really, at today's session. In the right top, you can see the basic components, depending on whether we have to do with a thermal or fast reactor. A moderator is or is not required for slowing down the reactors generated as a result of the fission reaction. Mr. Gudowski has mentioned this technology called HTGR. It is not a very new technology. As you can see, there is quite a number of reactors, including HTGR in Japan, under operation now. Some of them have been already decommissioned, like in the UK, Germany, elsewhere. There is the HTR reactor working in China these days, already mentioned by the others. This picture shows you just the reactors that are still operational or have been decommissioned, as I already said. But worldwide, you can now come across R&D on a variety of high-temperature technologies for the reactors by a variety of centers, one of those being X-Energy or USNC, the other one. Those projects rank among the most advanced ones. The latter refers to the ball reactor, being pebble-backed reactor, and the other type being block or prismatic core reactor. As for high-temperature gas-cooled reactor, because that's the full name of it, HTR being the abbreviation, or HTGR, depending on whether it is a high-temperature reactor or high-temperature gas-cooled reactor. Technically, it's a shorter or longer name, basically. There are two types of core construction. So as I said, again, PBR, which is pebble bed reactor, and the other one being the prismatic one, or block one, with a prismatic type of the core. The TRISO fuel is used for the purpose, as shown in the picture. Inside you have, for instance, uranium dioxide, which is a kind of grain in terms of its structure, a pyrolytic layer of diverse densities is the coating of it. Plus there is the silica carbonate. All this relates to the efficient products produced in the course of the operation of the reactor, obviously. The characteristic quality is that output temperatures attainable are tend to be quite high, and their usability for a variety of technological processes is diverse. Be it a block structure or a pebble bed structure, we need a moderator for the neutrons for such reactors, and graphite is used for the purpose. Steam temperatures, output ones, rank around 50 degrees centigrade. This shows you a very schematic, just indicative depiction of the difference between pebble bed and prismatic. Above, you have the pebble bed solution. The basic difference lying in the fuel. Well, in both cases it is triso, but in the first case they are formed into balls, whereas with prismatic or block, so-called fuel compacts are used, which are then transported into fuel blocks, which are then piled one above the other, as if, thus forming a core, the core of the reactor, to be specific. Here you have models, on that small table, but let me mention them later on, if the time allows. Characteristic about high-temperature reactors is, among other things, high security and safety of the reactor because of the structure of the triso fuel, first of all, and because of the structure of the core itself. In case temperature rises, automatically the power of the reactor due to the temperature rate or temperature coefficient is decreasing. The coolant is helium, which is chemically neutral, doesn't react with the chemical elements of the core. Simply put, there are neutron absorbers provided, which are due to absorb thermal neutrons if needed, and heat is received, generated and received, even if the coolant is lost through transmission and radiation, which is a passive function. A passive function means that whenever the coolant is lost, for whatever reason, like the pipeline being broken down, interrupted, there's no helium in the circulation, there's no risk, therefore, of an infinite increase of the temperature within the reactor. As simple as that. Once we regard high-temperature reactors, their efficiency is 30%, roughly. Any electricity production process or generation process is burdened with some sort of losses or loss, because this is about the physics of the phenomena concerned. This is the nature of the things. The main task of such reactors is not energy generation. Energy can be a side effect or side product, but not the main task of the reactor, whereas thermal energy for the industry, yes, this is it. A simplified drawing showing you a high-temperature reactor with the accompanying loops or circulations rather. To the right you have an exemplary industrial plant or establishment. Energy serves or is served as an additional product with the use of waste heat, for instance, not as a core element of the operation of any such reactor. A more detailed depiction of the uses of high-temperature reactors include various sorts of industries like paper mills, nitrogen-based fertilizers, ammonia production, refineries, hydrogen production, and others. In addition, hydrogen production may conceptually be co-generated with renewables, such as, for instance, wind farms, or using the solar energy, so through FV panels. One of the sources of heat used in such a system for hydrogen production would be a high-temperature reactor in cogeneration with other renewables. A portion of the energy thus cogenerated might be used for nitrogen production, but not only, also for generation of electricity. And CBH Center in Świerk has already carried out a series of projects related to high-temperature reactors, those that mostly translate to the current activities, the most on-time ones, in terms of design, preparatory work. Includes the HTGR project, which I will mention later on. The other one being Gizmostratic HTR project, which we completed late last year. It was co-funded by NCBR and carried out together with the Institute of Chemistry and Nuclear Technology and the Ministry of Climate and Environment. One of the elements of this latter project was to prepare a preconception project for a research reactor due to prepare legal instruments, organizational and technological instruments to develop nuclear reactor technologies in Poland. Testing the instruments that we have at our disposal was part of it. Material research was included. Research into nuclear fuels was part of it. Institute of Chemistry and Nuclear Technology did this particular bit. And here is the blueprint, kind of the deployment of tasks, in other words, for the project. Our research reactor, as designed, 40 megawatt one, as designed as part of that project, was given the working name of Teresa, so HTGR Teresa. It's a conceptual drawing, mind you. A concept of use of the heat produced within the reactor was developed as part of it to demonstrate the technological processes involved, as well as to be used for the university campus purposes. This is important to the extent that this project did not actually end with the formal end of the project, but it's developed now as part of so-called technological description of the research high-temperature gas-cooled reactor as financed by the Ministry of National Education and Science of the Republic of Poland. So, this includes research, conceptual effort, focusing on the target 30 megawatt, now 30, as reduced down from the initial 40 megawatt research reactor. In parallel, material research is being conducted, you can say. Our purpose is to prepare the core project as well as the safety and security concerns and aspects around the reactor. The concept was developed along the lines of the aforementioned project called Gospostratek HTR, as well as in cooperation with the Gemini Plus pan-European project. Now, at the NCBJ, we are working on, well, take a look, if you can, on that table, not far from me, 3 elements have been printed, 3D printed, to be specific. There's a scale of 1 to 2 for the use for the element, such as the one used with the HTGR reactor. It is namely a unit with holes for control rods. The other features that you can see are 2 different models. If you prefer, if you like, you can just take a short walk and look closer at it. Now, later on, however you prefer. Fuel unit, fuel block, a Japanese solution design is part of the project. I'm not sure if you can see it from far away. There are models of the fuel elements inside. They are detachable, or at least you can slide them to and fro. There is also a fragment, a model of a fragment of the unit, which has been printed, 3D printed, to show you, to see how the catchers for transportation of individual units are operated. HTGR, the basics of it I have now covered. As regards project implementation and development of the technology in question, attempts to do so, they have become feasible because the technology has been made part of a variety of strategic documents. So the contract and implementation of HTGR project have been implemented in cooperation with the Japanese Agency of Atomic Energy, or nuclear energy maybe, which is Japan's reactor operator. The assumptions behind the Świerk-based HTGR research reactor. The reactor demonstrates the technologies, low power technologies, usable in chemical as well as fuel industries. The structure of such a reactor has to be made in line with the requirements of the Polish market requirements, and it should combine the features, the characteristics of the industrial and the testing reactor, as well as its similarity to a future transmission reactor. The research reactor will probably be located within the Świerk campus. Japan Atomic Energy Agency is the operator of this particular reactor, as I mentioned before, and the core is situated underneath the ground, basically. Preconception project. The preconception project was implemented as part of the Gospodstratek project. These days we are implementing the basic project. The conception project has been completed as part of HTGR project completed last year. At the moment, works are ongoing on the basic project, as well as the initial report on safety and security, which is due to be completed by the end of May 2024. We cooperate and collaborate with industrial partners, and we remain open to new partnerships based on cooperation, collaboration, which includes the aspect of demonstration of our research reactor in Świerk. If you're interested in more information on more details on high-temperature reactors, basically I invite you cordially to the YouTube channel for a series of lectures and videos. I have made contributions along with my dear colleagues from NCBJ. Individual elements of the reactors are discussed there and shown in an indicative way, in an attractive way, I would say thus. Thank you very much indeed for your attention for the time being. Thank you very much indeed. Any questions? Agnieszka, don't escape yet. We have, based on what we can hear without the mic, we have rather powerful combined heat and power plants within the area of Warsaw, including Żerań, including others. And we are going to throw coal out of the area. On the other hand, if there is an agglomeration of more than 200 people, whose population is more than 2 million, more than 2 million, it's sinful to use coal. Well, I'm not that religious yet, but I haven't yet heard from any one of you referring to small modular reactors, whatever. I haven't heard about any concept of how to approach the Warsaw authorities in terms of how to implement SMRs, how to implement the technology that has just been covered, mainly HTGR and so on. I've heard about designing high-temperature reactors mainly for industrial heat purposes. However, we have to be careful in the first place about developing, and we have to place a bet on, and we have to focus on, this is what I mean, on cogeneration. If we deal with good old units at combined heat and power plants such as Siekierki within Warsaw, we have a capacity of about 80%. Come on, it's a very high capacity. In Świerk, you should also have a place, a room for a reactor that would start up the heat, generation of the heat to be transmitted into the district heating system of Warsaw. The project looks very nice, but is it practical enough? Well, I take it for granted you have identified the problem. Okay, I accept that. Very briefly, to address your point, I am fully in agreement with you. Yes, it is worth to use such reactors for cogeneration purposes. However, every such reactor has its own parameters, conditions, and can be used for a variety of purposes. High temperature one, in my opinion, maybe Professor Kutowski or Kozłowski would oppose this statement, but in my own opinion, to construct such a reactor just for heat, district heating, would miss the point, because thus we would lose what we can use for other purposes, for the benefit of our purposes. So waste rather than source, to be used as waste rather than source. Mr. Gutowski, we have persuaded OSG to our concept of non-single watt wasted. Every single watt to be possibly sold, used, utilized. There is no waste heat, mind you. That's a wrong name and bad sounding name. However, Agnieszka is right in stating that first such a reactor has to use high quality heat, and only as a second grade or second step can we use it for other purposes. But I can guarantee to you, sir, dear sir, that no single SMR would go wasted in terms of not in terms of any single watt generated being possibly wasted. Never ever. Yes, but how about how about replacing old 200 megawatt almost obsolete apparently units? How about replacing them? Obviously, many of them are working well. However, there are heat plants combined, hidden power plants, just heating plants, which produce lots of pollution, and definitely generation, cogeneration is required for the purposes in order to optimize the mainstream, the production, the generation. Now, we can open the point for further discussion. TRISO fuel, very well resilient, very much resistible, recyclable, if possible. Is it also, with all its qualities? It is not to be. TRISO is not to be subject to recycling. Sorry. It is used precisely so that the recycling step is omitted. No recycling. This is exactly how it works. So let's go further up. Now, Piotr Walczak will be kindly asked to accept our invitation to take the floor. Senior specialist with synthesis, Orlen Energy, responsible for BWRX-300 as a part of the fleet of the other reactors, and he graduated from the Warsaw University of Technology. Thank you very much indeed.
Good afternoon, ladies and gentlemen. Yes, my name is Orlen Synthos Green Energy, and being guided by the rule, as I was here, we're behind the schedule, so I'll try to be on time. Orlen Synthos Green Energy is a joint venture company between PK and Orlen Synthos Green Energy, set up in order to build and commercialize the fleet of nuclear reactors based on BWRX-300 technology by Hitachi. PK and Orlen is one of the shareholders. Don't have to introduce them. Largest company in the region. Great, very experienced in international projects, and Synthos Green Energy company of the Michał Sołowow Group, the largest Polish industrialist, owner of Synthos, Barinex, Sanit brand names, backed by technology, expertise and great determination to implement the project. So it's a strong partnership based on solid foundations with great prospect to succeed, and we are working towards that end. I think we all agree here that we are in the process of a next nuclear energy renaissance, and we hope that it won't be stopped by anything. The previous one was slightly slowed down, and one of the driving engines behind it are small SMRs. As Professor Godowski has already mentioned, about 80 separate projects being implemented in 19 countries. Even though BWRX-300 is a fully fledged SMR, it's characterized by slightly different features, and it's sticking out or standing out of others SMRs. It's that of 3+ generation based on tested solutions. While all the other projects are very interesting, many of them are based on solutions from the past, but never implemented. BWRX-300 is a technology, RX-300 draws from earlier solutions, so it's an evolutionary item. X in the name provides its 10th generation of boiling reactors offered by GE Hitachi. So these reactors and electric power plants based on them have high probability to be implemented, because 90% of the chain in the systems used in such power plants have been already tested earlier by industry, so they don't need separate licensing and separate development of the supply chain. About 30 countries are interested in the development of this technology, and it takes about 10% of the area of the classical nuclear power plant, up to 10,000 hectares. Of course, it depends on location and its feature, depending on the power of the coolant inlet, but we're talking roughly about this area. So the possible implementation of such a reactor are very high, because it doesn't require much land. The first project, first of the kind, to be made operational in 2028, is very much advanced, is being built in Canada. Canadian investor of Ontario Power Generation, Darlington, and under that project, the investor has submitted application last year for the building permit to Canadian regulatory license to construct. That's called in Canada, how it's called in Canada. So the construction should start very soon, and commissioning in 2028. This power plant is located only 3 kilometers from about 180,000 city Ottawa in Canada, so it's good information about possible locations of similar power plants or power plant in Poland. Success factors or potential success factors. One of the key elements is experienced partners in the project. First one is GE Hitachi, company that for 60-70 years has been building nuclear power plants, one of the most experienced in the energy. 67 units they built in 10 countries, about 40 still operational. Ontario Power Generation, as I said, investor for the first project based on that technology, one of the largest energy companies in Canada, great expertise for this first of the kind project. Tennessee Valley Authority, the largest public supplier of electricity and operator of nuclear power that plans the implementation Cleans River in Tennessee very soon. And with these companies we collaborate. And in March we signed the technology cooperation agreement, TCA, which, based on the first project to be implemented in Canada, to create a standard design for a nuclear pipeline based on BWRX-300, which will take into account Canadian, American, Polish and European requirements at the starting point. It won't be that it's one-to-one copy and paste in Poland, but at this very start, we're working on that we include as many requirements so it's be as versatile as possible in order to shorten the licensing and implementation process in Poland. It's TCA is for $400 million, so it's a serious liability and obligation and an amount which will allow to push it forward to become local. It's a precedent, a Polish company taking part in designing a nuclear power plant with its influence on the solutions and learning from more experienced Canadian and American partners. The second component, very important, is the funding. In April, Exim Bank and TFC from America have announced possible support to up to $4 billion of the project, so to build fleet of BWRX-300 fleet by Synthos Green Energy. PKO, Polish banks and Santander are interested in it. We also work and we have initial agreement with the National Environmental Protection and Water Management Fund. So at this stage, obtaining declarations and agreements is the best gauge for the feasibility of the project, and it's a serious matter. Small nuclear energy and the program can be the key for energy transformation in Poland, and it may contribute to Polish economy being modern and competitive. And it's not possible without the support by the state. And it was declared during the conference we held together with our shareholder on 17th of April. We organized this conference and we presented a prospect location for the future nuclear power plants based on BWRX technologies. Are potential initial preliminary locations being the result of many months of the team's work with support with independent advisors such as Geophysics Institute of Polish Academics, Mining Institute and Agroprojekt Katowice. For these locations, we shall continue localization and environmental assessment, and only then we'll know whether it's all feasible. But at this stage of the project, there are no contradictory factors that we don't work. And to answer your question, also Warsaw and Kraków are on that map. We can divide these prospect locations into 3 areas. Energy, the locations such as Ostrołęka, where the main product and driver of for locations electricity generation and supplying into the grid. Industrial locations like Włocławek, Nowa Łagonica, Tarnobrzeg, and so on, where other than generation electricity, we can treat technological heat for the industrial plants located in these respective areas. Third category, heat generation, heat provision other than electricity, also in cogeneration for heating purposes. So we are working on these locations and we built also we'll announce other locations following the progress of our work. Our work and the development of wouldn't be possible without local partners who operate in those areas. And as for Ostrołęka, we have with Energa, Włocławek, Anvil, Warsaw, PGNiG, Stawy Monowskie work with Synthos, Nowa Łagonica, in Kraków, ArcelorMittal, in Kraków also MPC, and Tarnobrzeg and Stalowa Wola with Industry Development Agency and Special Economic Zone. Being aware of how important involvement in the beginning of the project is, we had the BWRX-300 Introduction to Technology workshop for Polish institutions, stakeholders who will be involved in the process to provide of licensing and implementation of the project in collaboration with our technology provider. The keynote speaker and moderator was the one who had the idea of this technology and key designer. So the workshop was very popular and people came in big numbers. We had an opportunity to discuss a lot, and based on that and other activities, we are in dialogue with institutions that are going to be involved in the licensing process. April was quite busy for us, like any month, but many things have happened outside. Amendment of Special Act, Nuclear Act was amended, based on which we are going to operate. Also, this technologically neutral law, now the solutions streamlining the investment process have been added. Based on this amendment, the institution decision was shifted to the very beginning as the first decision in the process, and by the end of April we submitted in the Ministry of Climate and Environment 6 applications for this basic decision to build nuclear power plants with BWRX-300 reactors for the locations mentioned above. Driving towards the end and to wrap up, I would like to present the progress of work and where we are right now. Orlen's the Green Energy OSG has been operating for about a year. We'll have our first anniversary soon, and we've managed to do quite a few things, but a lot is still in front of us. We are aware of how lengthy, how difficult the process is. Last year we've submitted an application to the Polish Atomic Energy for an opinion about the technology, so we started the pre-licensing process. We hope we'll get the opinion soon, very soon. We've done the pre-screening of the usefulness of several dozen locations based on criteria defined by Polish regulations and guidelines by International Atomic Energy Agency, the president of the Polish agency, and the requirements of our technologies supplier. We examined several dozen locations with participation of the partners I've already mentioned, and from that basket we located a few. We announced in stage 1. We continue working on them. In parallel, work on the portfolio and preparing next locations, being aware of the fact that during the implementation there may be factors or developments that will rule some of these locations out. So the development of the portfolio is of key importance. For 3 locations, we start the environmental procedure. We prepare the cards and we are going to apply for environmental impact assessments, decisions based, and then the environmental decision for 2 locations. We started work in the field to specify the location. We are right before obtaining the general opinion. What's in front of us? Developing applications, analysis, input, and field work for the need of the key decision, and also environmental location decision, building permit. We are aware that only then we can talk about the beginning of the construction and then the commissioning and operation. So we're at the beginning of the way of the road. We know the scale of the challenges in front of us, but we have a very dynamic team that keeps developing and being determined to implement the project. You have to start even a longest journey with the first step. We've done even the few steps. Now, one more picture, and getting back to the technology, as I said, it reflects very well the fact that we face, in case of BWRX, we face evolution, not it's a 10th generation of reactors GE has been building for 60 years. And thanks to that, we are in the comfortable position that the project is feasible, implementable within the time and within the budget as planned. I think that would be it. Thank you very much for your attention. I'm ready to answer any of your questions. Yes. I would like to sort of continue. At the beginning, you mentioned that you've located, selected 7 locations. Now I've found that it's 6. There's no cooperation with Warsaw, as it seems, and the Warsaw milieu. So I must say that 10 years ago, in 2014, association, including Polish Nucleonics Association, adopted a resolution on giving up that it's necessary to that Vattenfall should abandon the coal-fired unit to generate heat at that time. And under our pressure, as you know, Vattenfall gave it up. We've managed not to build a coal-fired unit, but already then Warsaw groups wanted to build but the power plants to be built with big one. New Warsaw would give prion heat cogeneration to the heating grid. Why didn't you manage to arrange for collaboration with Warsaw as well, so that the topic and it's most urgent and the best in a way, because it's the best conditions to make reservations? Well, let me correct. We have very strong cooperation. We think about Warsaw. We haven't submitted the application for the decision in Warsaw because we haven't selected precisely location within Warsaw. We are working. We examine different possibilities. So we'll continue to develop the project for Warsaw for sure. Sorry, someone's speaking off the microphone. Can't hear a word. On the list of possible locations, didn't see Puławy with fertilizer plant, huge fertilizer plant. No. Well, no, cooperation with various, I mean, we work with various technological partners. We try to establish partnerships with, but I'm not allowed to mention everything. Any other questions? We have a couple of minutes left. I have a following question. How long is the training for operators, and how many do you need? You need 100 people per unit, and training for. I'll ask for support, Professor. It's not my field of specialty. Operators, 90 weeks, 18 months. 100 people per 1 reactor, so 70 if you have a fleet of 4 reactors. So when we increase the number of it, you can have one team that will service things that for 1 reactor you have to have permanent staff. Well, it's very simple actually. 24. I didn't hear the question. It was off the mic. Operators. 3 shifts. So it's not that you need physicists. So 20-30%. All mechanics, electricians, chemists, chemical engineers, and so on. So, of course, physics maybe are most important, maybe, but not they don't come in the biggest numbers, most numerous. Thank you very much. One more question. I wonder whether one location means one reactor or more, maybe two. And do you plan for a capex? What would be the capex for one reactor for today? Of course, in today's terms, one location doesn't mean one reactor. We try to get the economies of scale. As to capex, it's not. I mean, I'm not authorized to talk about it. We have the numbers, and I think soon they will be presented. Unless we can give you this. You can add, there were 4 independent assessments, including the Canadian Working Group, Boston Consulting Group, Ernst & Young, and capex is between 1 billion to 1.5 billion, depending on different euro. Sorry. One thing, as compared to a gas-operated unit, let's say emissions is like 90 euro per ton, and it will be more. A reactor or 1.5 can be built with economized money on emission within 25 years, and the reactor has a life cycle of 60 years. Thank you very much. Let's move to the next presentation. Andrew Halfman will be online with us via internet.
Just 1 second. Can you say something? Can you can still hear me? Okay. Let me know when to start. All right, very good. Thank you, everyone, for attending, and very good afternoon. Apologies, I was not able to travel over in person this week. We have some customers in town, OSGE, and was unable to travel. So I wanted to spend a few minutes talking about the GE Hitachi BWRX-300 Small Modular Reactor. To start with, GE Hitachi, we have a very rich history of nuclear. You've probably heard some of the conversations about the vast depth and experience that GE Hitachi brings. We started this business a little over 60 years ago. 1955, General Electric established their atomic division. One of the things we're most proud of, in 1957, GE received the first Atomic Energy Commission license for a commercial nuclear power plant. That was our first plant out in California. 5 years later, we achieved first full reactor power for a first Canadian project. And you can see the timeline progressing, 25, 50. We now have 67 BWRX-300. This is our 10th generation boiling water reactor with a net electrical output of approximately 300 megawatts. A technology selection program with Ontario Power Generation, and in 2021, the BWRX-300 technology was selected by Ontario Power Generation to be deployed in Canada. What the BWRX-300 is, some of you might be familiar with other large boiling water reactor designs, such as what is shown on the left here, what was referred to as the Economic Simplified Boiling Water Reactor. This was a design that went through the early 2000s, was fully licensed, but never deployed commercially. We took that footprint, essentially reduced the volume by 90%, and developed the BWRX-300. As I said, this is our 10th generation boiling water reactor. All of the technology is proven, and it's scaled from our previous and licensed designs. We essentially have 50% less concrete per megawatt than existing large-scale nuclear plants. We do leverage, and I'll talk about this more in a few minutes, commercially available fuel. We believe this certainly differentiates GE Hitachi in the marketplace as opposed to some other, what could be referred to as startup companies coming in. We are fully capable of integrating with renewable power. We are also fully capable of integrating with other electricity, or excuse me, integrating with non-electricity producing applications, which includes district heating, process heating, as well as hydrogen production. We have started and are partway through the licensing process, not only in Canada, but we're also very far advanced in the US. And one thing that's very close to me at this time is our licensing is well underway within Poland. We do expect the first BWRX-300 to be operational in Canada by 2028, with fast follow deployment at other locations throughout the world soon thereafter. The BWRX-300, as I said, it utilizes proven technology Therefore, we don't have to do any demonstration projects. We don't have to test any new materials, processes, or components. As you can see, if I work around the page here, the heart of the technology is the reactor pressure vessel. This is the same material, same fabrication processes as advanced boiling water reactor, the ESBWR, and most of the existing BWR fleet today. The diameter of the reactor pressure vessel, it is the same size as the Mollberg plant, which has been in operations since, I believe, the 60s or 70s. BWR technology, it uses a chimney. This uses this uses the same ESBWR technology, which is actually or was in use at Dodvard, very simplified from existing designs. The fine motion control rod drives, these are the exact same components that are in use today in the ABWR and ESBWR. Similar for control rod blades, shifting now over to the left-hand side. These are the exact same as the existing nuclear fleet, the exact same as the ABWR, slightly longer than ESBWR, almost identical to the existing fleet that's out there today. At the top of the reactor pressure vessel, we have steam separators and dryers, again, based on the existing ABWR and ESBWR technology, nearly identical to the Mollberg plant again. And then one thing we're most proud of is the technology will utilize GNF2 fuel. This is an existing product line that here in Wilmington, where I'm at today, we have fuel bundles coming off the assembly line. Since essentially the 1990s, GE Hitachi has delivered over 25,000 of these fuel bundles, and they're utilized by 70% of the BWR fleet. To put that in context, GE Hitachi does not have to go through a qualification program to qualify any type of new fuel. This would be existing fuel that can construction. You can see in the roughly center of the graphic here, the reactor building. It's largely and ease of construction. One of the key things for us is being able to construct this unit, and we are designing cost as a key factor into the design. You can see largely on the right-hand side of the screen is what we refer to as our reactor building, largely underground. This utilizes proven construction methodologies and techniques from other industries. This comes largely from mining industries, as well as underground technologies that are existing throughout the world today. We utilize steel bricks, which essentially are a steel concrete composite that make up the reactor building. We maximize the use of catalog items, such as off-the-shelf valves, piping, and heat exchangers. And then one of the things we're also most proud of as General Electric as a whole is the turbine generator set commercially available today. This is an existing technology and design that's utilized throughout the world with no design modifications or upgrades required to be able to partner up with the BWRX-300. This shows a rendering of the plant itself. It's a very small footprint, very compact and simple plant layout. You've probably seen some other marketing and advertising materials, but what's referred to as the power block, which houses the reactor building, turbine building, rad waste, and operations. This entire footprint would fit roughly on the same size as a football pitch. As I mentioned earlier, we are optimized for not only electricity, but other industrial applications. As I mentioned earlier, we can do hydrogen production, synthetic fuels, district heating, water desalination, and we can provide process heat, process steam to the industry as well. Going through some of our customer selections, I spoke of this earlier, but Ontario Power Generation in December of 2021 selected GE Hitachi BWRX-300 as the technology partner. This is actually under construction now at the Darlington New Nuclear Project. We expect deployment could be as early as 2028. We are very rapidly progressing through the licensing aspect of this. We have submitted a license to construct application to CNSC, which is the Canadian Nuclear Regulatory Body. And the X300 provides substantial economic opportunities, not only for Ontario, but the entirety of Canada. Sask Power, which is another utility in Canada, similar process. They went through a very rigorous technology selection process, and in June of 2022, GE Hitachi BWRX-300 was selected. This was after a multi-year assessment of numerous reactor vendors. This focused on safety, technology readiness, and fuel type. Karnfol Next, which is in Sweden, similar. They went through a technology selection process. We successfully won that for deployment in Sweden and Denmark. We are looking to supply a number of BWRX-300 units throughout the region as soon as possible. And then finally, customer I work closest with, Orlen Synthos Green Energy. There was a joint venture formed between Synthos Green Energy, PK, and Orlen, two very substantial and large companies there in Poland. We are partnering with them to develop and deploy a fleet of BWRX-300 throughout Poland. You've probably heard recent announcements, and if my good friend Professor Vauclaw is there in the room, I'm certain he's talked about the 6 site selections that have been made by OSGE for deployment of the BWRX-300 technology. And then in closing, we have a very simple, cost-competitive, small modular reactor design. We are an ideal solution, not only for climate change, but also for energy security. And sitting here today, we are ready and able to move into commercial deployment. I believe that's all the slides I had. I wanted to thank you for the time and opportunity to present, but I will pause, stop sharing my screen specifically, and entertain any questions that the audience may have. Oops. Okay, no worries.
Bardzo proszę.
One comment, if I may, but please use the mic, sir. Please use the mic. So that we can hear you in the booth.
Trafiło się nam, a właściwie Polsce, jak ślepej kurze ziarno. Proszę Państwa, General Electric to jest chyba największa firma na świecie. To jest firma przebogata. Ona ma banki, ona ma wszystko. Taka firma na Zachodzie i u nas w Polsce nie może się jakoś poślizgnąć nawet. To jest wielka szansa dla nas. I dlatego bardzo polecam, już z Panem wymieniłem wizytówkę i będziemy też i dla Warszawy kontynuowali, żeby było dobrze. Dziękuję.
Dziękuję za komentarz. Przetłumaczyłem część komentarza. Jakieś inne pytania?
Anything else? Thank you very much for this commentary. Any other comments? Based on what I understood, the structure in Darlington, near Ontario, Ontario, was the first one, and there are going to be more to be licensed. So not until Darlington is completely built, the process in the other possible places will not be developed, right? Is it so? Sir, I've already translated that.
Darlington New Nuclear is our lead project. We have at least 3 other projects underway at the same time. In the U.S., Tennessee Valley Authority has selected the BWRX-300 technology. They are rapidly moving through licensing phases as we speak, and they expect to break ground on their units sometime in the next 2 years. And then within Poland, we are not waiting. OSGE, they want to be a very fast follower to the Darlington project. So in essence, short answer, we do not have to wait for Darlington to be completed before we move into other projects.
Tomku, ja mam dobrą tutaj informację dodatkową. Znaczy dobrą informacją jest to, że Państwowa Agencja Atomistyki ma teraz umowę z kanadyjskim regulatorem, że będą robić tak zwany joint assessment, także ten proces może iść poniekąd, może nie całkiem równolegle, ale prawie równolegle. Także to są dobre wiadomości i im więcej będzie współpracy między regulatorami.
So this is going to make the thing good for both parties, apparently.
Dobrze, dziękuję bardzo. Zamykam sesję, a jeszcze jedną, proszę bardzo.
Thank you very much indeed. There's one more.
With so many orders and interest in the reactor, what do you see as the biggest bottlenecks for you to kind of truly expand the nuclear industry for your part?
Just to repeat the question back, it was a question about what do we see as the biggest challenges or bottlenecks to deploy. Is that correct?
Correct.
So honestly speaking, one of the key challenges that not only GE, Hitachi have to overcome, but the broader nuclear industry has to overcome is supply chain. You know, you're looking at industries that, even though some new nuclear has been built in recent years, the scope and scale that's being talked about, not only at GE, Hitachi, but other vendors, is something that the industry essentially has never taken on before. So standing up those capable supply chain partners to be able to produce multiple reactor pressure vessels other components that go into these plants essentially at the same time or in parallel is a known challenge that we have to overcome. Some of the steps that GE Hitachi is taking is we are looking at a very broad and diverse supply chain, not only in Canada, but also within the US, Asia, and Europe, so that we can have multiple points of supply of these key and critical components.
Dziękuję. Thank you.
Thank you very much indeed.
Wacław ma.
Wacław,
ja chciałem jeden komentarz dla młodych, ponieważ tu wielu padło słów o...
something for the young generation. Christer Dahlgren, whom you have mentioned, who has been a main constructor of the BWRX. He was not rated the highest as a student, you know. 30 years afterwards, he, however, became the main constructor. And he once migrated from his native Sweden into the United States. Just for you to mind. Thank you very much indeed. Let me close this session now. Thank you very much for interesting inputs and intense discussions, and see you then tomorrow morning.